So now we are officially in session. Welcome everybody once again. And what we'll do basically is to start our course right now. This course, we all know, is a design course. In this course, we cover across technologies. That's LTE, UMTS, and DAS. We explain during the by the end of the completion of this course, you guys will able to understand and also do the design of overall design of this course of radio network, both macro sites and DAS sites. So how we have devised this course basically is we have different chapters of course. We'll give you a more in-depth understanding of what this course is trying to do before we move on to the first information part of this course. So this course basically provides practical knowledge about cellular design network. What we are doing over here is basically without going distributing our course based on technology that this is only for LTE or this is only for UMTS. We are overall putting putting in the end-to-end design process. I can hear somebody's background noise. Okay. Okay. End-to-end design course. So basically what this course is doing is providing you the design knowledge for LTE, UMTS, DAS networks end-to-end. So during the course, you will able to see both macro and DAS network. As in this slide, you can see this is the overall framework of how this course will go. We have if you have a basic understanding of any cellular network, it has macro sites, it has DAS sites. DAS sites have been in deployment lately, but it is a very booming field right now. But either macro site or DAS site, it has some basic body of knowledge which is shared between the two. And then there's some things which are different between the two, like the process itself is different, the design tool which is used for DAS or macro site is different, how we prepare the RFDS or design sheets. What is RFDS or design sheet we will learn during the course of this session or the course of this whole training course one. So what is R&D CIQ we'll learn, but what is the process followed to reach the RFDS or R&D CIQ in different scenarios, if the site is 2C or 3C, or if it's a DAS site, if it's a DAS 4C site, or if it's a macro 4C site, how many sector it has. So and what tools it requires. It requires design tool for if it's a macro, it's a tool, and we'll see how a tool works. We'll see how IB wave works. We will not have the hands-on for ATOL or IB wave because it's practically not possible in this budget of the course. But we'll have the sessions and videos to explain step-by-step process what ATOL is used and how ATOL is used, and there are videos in which this ATOL training is covered and IB wave training is covered using videos. And then we can have later on if more detailed sessions, which will be out of this course hours. But in this course objective, you'll completely able to understand how ATOL works, what is its role, and how to use basic functionality of ATOL and IB wave for DAS sites. So what this course is basically doing is it's getting you RF basics, it is giving you design concepts, it's getting you introduction and very close to hands-on knowledge, but not hands-on knowledge, but of planning tools. You will know how to prepare RFDS for any macro, DAS, 2C, 3C sites, and the R&D CIQ, and how the R&D CIQ is prepared and what is their role in this overall design process. So so far, any of you guys have any questions? You guys can type or raise your hand. Usman, do you have any question? You can type, Usman, or you can
Okay,
just
but you
put your
unmuted.
question up. Yeah, put your question up.
Okay, my question: do we need to install any softwares in order to do something or understand it properly? The reason I'm asking because I actually worked the night shift. I just woke up. I just like 2 minutes ago I did the registration and I'm like totally blank. So I haven't even gone through the prerequisites that you sent.
Okay, no, you don't need to install any softwares.
Okay.
So you don't need
But
to install any software for this course. So unless until just make sure the Citrix standard platform on which we are conducting this training is working fine on any of other machines if you want to use it later on. That's it, nothing else. Okay.
okay.
So what we have is basically in our overall that is our goal of this training. Before we jump into the end-to-end process of this training, there is a very important slide of end-to-end process. Alila Ari has a question. What is this question? Is there any way to get a tool or IBWay for hands-on training? Uh, no. For me, no, there is no. Their license software, their cost runs into thousands of dollars. I don't know otherwise anyway, unless somebody is willing to purchase them. Uh, okay. So, these are the 5 fundamentals outlines you can say which this course will be delivering. Before I jump into the process or the end-to-end process, how this course is designed based on the workflow, before I explain that, I just want to refresh in your guys' memory what is the UMTS architecture, what is the LTE architecture itself is. And so in a cellular network, there are many domains. There is a UTRON or the radio network, or there's a core network. So radio network and the core network are always there. Either you're talking about UMTS, LTE, or GSM, or CDMA. Any technology, which is a cellular technology, has a portion of the core network and the radio network. What happens basically is in different technologies, UMTS or LTE, the component changes between core and radio network. The jargon changes. Jargon, when I say jargon, it means in GSM, the node B was in GSM it was called BTS, radio base station. RBS and UMTS is called node B. In LTE it's called E node B. So these there used to be a RNC in UMTS and the BSC in GSM, but no more there is any central controller in that sense in LTE, but there is still something called MME, which we'll look into. So what, as an RF engineer, if we look at LTE or UMTS, we will see the region which is highlighted in red is our domain. As an RF engineer, we should know about all of those nodes. Uh, the thing is, if I try to explain you how, if you're able to see this portion, basically, let me put on my pointer on. Okay, you see this portion is basically, which is marked in red, is RF. This portion is the main domain of RF engineering. This is called air interface. Okay, this air interface is basically what RF engineer, most of his job is about. As you move away from this air interface, you will find that we should know about node Bs or e-node Bs. We should know about MMEs and RNCs. So what basically uh, what basically the job of an as an engineer is to able to design the air interface, which is between the UE and the node B, or the base station. We should know how the node B works, what kind of node Bs are there, what are the capacity constraints. Uh, Note these two words. There is a what is baseband capacity and what is radio capacity, because these two words you should understand very well. And during the course, during this course, we'll be learning what is baseband capacity and what is radio capacity and how it's dimensioned, because this is an important part of RF engineering. And how the RNC is dimensioned is also part of RF engineering. So this is basic explanation. For many guys, they already know it. As I said, for a few guys, this is a new thing. But to take everybody together, this is something which needs to be explained. So what we'll be doing, we'll be learning more about RF engineering in the domain of UTRON or EUTRON. We will not be very much familiar with the MME, but we'll know what's the role of MME is when we'll learn LTE, what's the role of Node B is. So let's talk about UMTS itself. In UMTS, we have RNC. RNC is connected with the Node B. RNC is a radio network controller. RNC has three functions. You can note down the three major functions is mobility control, traffic routing, and traffic integrity. These are the three functions of RNC. When I say traffic routing, the traffic routing between the base radio network and the core network, that's the job, one of the three jobs of RNC. So that was how UMTS architecture was planned. RNC had a very important role. So now what they did in LTE was basically, of course, the air interface technology was different in LTE. What they basically did in LTE was they that out of the three functions, which were traffic routing and traffic integrity, they handed them over to eNode B, and only the mobility control function was left to be controlled centrally, and that was delivered to MME, or which is called mobile mobility mobility management entity, MME. So the role of this central body MME compared to RNC is much smaller in LTE. And the basic difference between the two technologies, UMTS and LTE, is its air interface. UMTS used air interface WCDMA, and LTE used air interface OFDMA. So these two are totally two different air interface technologies, and which makes the efficiency of the spectral efficiency, noted down this word as well, spectral efficiency of the two technologies entirely different. And why the companies are going from UMTS to LTE is basically because of the higher spectral efficiency. We should as RF engineer all understand that spectrum is a very, very important resource in RF engineering or cellular network engineering. The more efficiently you can use the spectrum, the better network or the better throughput you can give to the end user. And that is the one of the most basic reason we see the progression that we were using AMS, then GSM, then UMTS, and then now LTE, and we are talking about advanced LTE already, because the technology is progressing and more spectral efficient technologies are being adopted. So far the LTE is considered to be the most spectrally efficient technology, which means it can deliver highest data throughputs to the end user, in simple words. So now we understand the two architecture of the two technologies we'll be covering. Besides DAS, DAS is not an air interface technology. For your information, you guys should remember that it's not an air interface technology. It's a signal distribution technique. You cannot even call it a technology in itself. It's a technique or a repeater in itself. So what DAS essentially is a repeater, but to deploy it is very strategic. It's very costly, and it requires a lot of design consideration. That's why this has become a field in itself. DAS stands for Distributed Antenna System. We'll be discussing that and understanding the basics of DAS and macro sites during this session. So within this session, what we'll understand how the overall course flows, what is DAS, what is macro sites, and how they are designed and how the process works. That will be the part of that course in the sessions to come. But what part of our knowledge will be covered mostly in this session, and how part will come in the sessions to come. What and how goes together, but in this course you will have a good understanding of how this course will be delivering you all the body of that knowledge. Okay, so coming to the process. So if I simplify the process, means highly simplify the process, you can easily say that any RF engineering of cellular network, whether it is UMTS or LTE or DAS or even GSM, the old legacy technologies, they have basically three major steps in the design process or the planning process. So design or planning in RF engineering are used interchangeably. When you go more, then you will find some of the companies have design department separate and planning, but it's very rare. But design and planning is basically the word used interchangeably in RF engineering. So what is the step one? Okay, there is a preliminary design, then there is a radio frequency design sheet, RFDS, and then the third step or the final step of any design process is R&D CIQ. Or radio network design customer information query. Okay, so these are the three fundamental steps. Nobody can disagree. It's generally or vaguely these are the three major steps of any design process of a cellular radio network of LTE, UMTS, or DAS. Now, if I go into the detail of each of these boxes, you will able to see that it looks something like this. So how the RF design process looks like. So basically what I can say is these are three boxes represents the, not exactly but vaguely, the three steps. This is, you can say, step one. Okay. Sorry guys, I'm having problem with using this drawing tool. This is step one. For this, I would say that till here it is step two. And this portion itself in itself is a step three, which was described over. So if you are able to see what is this step, what do we have overall over here? So basically this portion is not the design portion. Once you are done with the R&D CIQ portion of the course, you will see that scripting is not part of RF engineering, and where we come in play is basically after this portion, which is somewhere over here, and we call it pre-launch optimization. So basically design cycle ends essentially at when the R&D CIQ of a site is done. Okay, so when the R&D CIQ of that any site is done, we are done with the design of that site essentially. So now before I move any further, we'll go to each of these sessions. You can see over here we have a design requirements. We everything starts with our design requirements. The design requirements come in from the budgeting team uh, or the team which is planning or budgeting the whole network. So, and the standards like what kind of coverage is required is part of the design requirement. What kind of quality and what kind of throughput is required is part of the design requirement. When the design requirements get in the tool, we are able to calculate for a given city or given place the number of sites. That number of sites is basically a rough number estimate, which is usually part of a nominal design. You will see people saying using these terms somewhere or somewhere not. So, which is basically a part of nominal design. This design is even before preliminary design, and what is it's just ideal design, and the main purpose of that design is to have idea of number of sites, so it can be budgeted, because budget is very important for any commercial activity. So they need to estimate what is the cost to provide a given quality of service to the user. So they do a preliminary design work that usually is done at the national level and not at the market level. That comes to the market level later on, in fact. So when the design requirements and number of sites is calculated, the overall design is comes in. Where is the most mass of the job? So that design requirements and the budgeting is done by very few people. They are usually very much experienced. So it's done at a very high level usually. Where the market role comes in, or most of the RF engineering job which you see in the market posted comes in, are basically when when that design, which was an ideal design, has to be uh, implemented. Okay, when it has to be implemented, if the ideal design said, okay, the site height of the site is 30 meters, but actually when you go to a site, uh, it's on a rooftop, and you cannot install a tower, and it's 15 meter. So then you have to adjust the site. You have to accept it or reject it or adapt to the site requirement. So you have to actually redesign the whole site and put it according to the site. Then you do a detailed survey and tell what is possible or what is not possible. So we had a design requirements, we had the initial design. After that, we went actually to the site survey. Uh, and when we did the site survey and found what actually we can install or we cannot install, we reach a final portion, which is the RFDS, final RFDS. But before that, we have a portion which is called preliminary RFDS, which is a part of the design. So at both the stages, we should remember we are using planning tool, which is ATOL, IB Wave, or ASSET. Well, I got the question, can I explain more the site surveys? Uh, I will explain the site surveys in details when we will be doing the RFDS preparation, how the RFDS is prepared. So what are the inputs from the site surveys, what we are looking at site surveys, that will be later part. Right now, I'm just trying to give you guys a good grasp or bird's eye view of the overall design process. And then what we need to do, so you have a bird's eye view of where we will be going. So we have a preliminary design. We will be learning about ATOL and ASSET and IB Wave. So IB Wave is a DAS design, is used for DAS design, but also in DAS system, we still have a preliminary design based on the design requirements. And when this design comes in, we have a RFDS based on that design, and then we put it in the planning tool again. So we had a preliminary design, which was essentially ideal. It did not have any information. We went to the site and we found that what is actually is, we start preparing the RFDS and put it in our planning tool. If it meets our design objectives, that becomes automatically final design. But if that's not the case, our design objectives were not met, then we'll go and put the data again in the A tool, and we'll replan it and we'll run some iteration. When it meets our design objectives, we'll say, okay, all the coverage or throughput and the quality design objectives are met. And this will, based on that, we will prepare our final RFDS. RFDS is radio frequency design sheet. Once the RFDS is prepared, that's the second last steps in the domain of RF engineering. But RFDS basically what it contains. It contains site information, azimuth, height, all those details. It contains what kind of node B we will be using, what will be the antenna which we will be using, what kind of remote electrical tilts we will be having. But it does not contain some of the information like what PCI we will be using, what frequency exactly we will be using. That is not usually the part of RFDS. RFDS contains more about the site information like node B cabinet type, the height of the antennas, the feeder length, the feeder types. When I say feeder in RF engineering is basically the cable connecting the node B with the antenna is called feeder. So all those things are part of RFDS, but the soft parameter like frequencies, the scrambling codes, the PCIs, those are not part of RFDS. They are planned separately, means PCIs and frequencies are planned separately, and they are entered into the PCI, PSC, etc. And they are input into the RND-CIQ. And what basically is done, many information is input from other planning sources, in which we will be learning what are the other planning sources in this course, into the RND-CIQ, and we have a lot of information which goes from RFDS into the RND-CIQ. That then we have a complete RND-CIQ. What RND-CIQ itself is, basically, RND-CIQ is basically a way to translate the information of scripting to the scripting team or the UTRAN engineer. That UTRAN engineer or scripting engineer or integration engineer, how to program that node B or the radio base station, which can be node B or eNode B for UMTS and LTE, how to program that. All that information is captured in the RND-CIQ by RF engineer and send it to them, and they understand that document. That document is essentially an Excel sheet in a standard format, nothing else. It's an Excel sheet in a very specific format, which the scripting engineer and node B engineer can understand and script or program the node B according to it, or generate the scripts according to it. What RFDS is basically. So the main purpose of RFDS is to communicate with the site construction engineer, how to build the site, what kind of node B will be there, site installation engineer and site construction engineer, what will be the tower height and all those details. Using this RFDS, we communicate all the information about the site construction and installation to the construction team or installation team or site integration engineer. Okay, so basically RFDS and RND-CIQ are the ways of communicating with other departments by RF engineer, and they have to be in a standard format for other people to understand. There are many formats. During the process, we'll be learning what are the formats of RFDS. Of course, and one more thing, RFDS for macros, each of the site is different, separate document. Similarly, the RND-CIQ as well. But for macro and DAS site, you will find that there is a hugely different process to reach or the final RFDS of a macro site and a DAS site. They are entirely two different processes. But RND-CIQ still is very similar for a macro site and DAS site. Why and how, we'll discuss it in this course when we reach those topics. I received a question, what is PCI? If you understand, PSC is a primary scrambling code. It's used in UMTS, right? It's basically tells you, identifies or separates UE or the mobile equipment or the cell phone in UMTS identifies a cell based on cell ID and the primary scrambling code, or PSC, right? Similarly, in LTE, PCI is physical cell identity. This is basically very similar to what you can say is PSC in UMTS. No, PCI is just like PSC in LTE. Basic Basic is basically used in GSM, and PSC is more like frequency, or ARFCN in GSM. If you want to make an analogy, it's an analogy accurately. PCI does not represent a frequency band. In GSM, ARFCN represent a frequency band. So PCI is basically a convoluted code using which a UE, or user equipment, or mobile phone or cell phone identifies a cell, an LTE cell in LTE. So essentially that is, we will learn all more detail later on. So once this whole process is done, we send it out all the information to the Node B engineers. They script it, they construct it, the construction team constructed you based on RFDS, R&D team, the scripting team based on R&D script it. Sometime R&D team also requests for the RFDS for this scripting purpose, but that is not the essential requirement by them usually. And then they script it, and then they'll let us know, okay, we have integrated the site, come and audit. So then the RF engineers jobs again start, which is called pre-launch optimization over here. Okay, so it's pre-launch. Pardon my writing. So this pre-launch optimization is how it's done. It's totally different topic, different subject. It's another course of pre-launch optimization. Again, pre-launch optimization of macro site is done entirely differently than the DAS sites, or the distributed antenna sites. Whenever I use the word macro site, which means tower site or the rooftop site, we will see a lot of pictures in this presentation to come, that how we do it. So basically, we have already explained what are the fundamental steps. These are expressed in words. Fundamental steps of framework of radio network planning remains same irrespective of for macro or DAS sites. The framework, or the end-to-end steps which we discussed earlier. Also, fundamental steps of radio network planning remain same on both LTE and UMTS. The steps remain same, but design methodologies and the process between and technological considerations. Technological considerations, I mean, what is the signal level, how the signal will be distributed, all those things. They have a very big difference in case of macro site and the DAS site. In case of LTE and UMTS macro sites design, the design methodology share a lot of similar processes, similar technological considerations, but they are still not exactly same. You cannot say LTE and UMTS. Process is very similar, but not exactly same, because design considerations, the technology considerations are different in many important ways, in fact. Okay, we, as a part of this course, we also introduced to the different terminologies used in different operators within USA. So we were talking about the preliminary design and the final design, how it's done. Okay, can you guys give me a second? I have. Okay, sorry guys. Okay, sorry guys. So basically, what are the fundamental steps? So preliminary design, for example, in AT&T, it's called PICD, and final design is called ICD. Uh, PICD, I remember what was those words, but I skipped the acronym. Later on, I will find out and tell you once again what is PICD and ICD. But these are the terminologies. We are in our process. We are understanding it's a preliminary design and the final RFDS. But when you go in these organizations, they have made their own terminologies according to their requirements, and they use those terminologies. For example, AT&T use PICD and ICD. But if you go into T-Mobile, they have altogether different approach to it. The process is still the same, but the approach is a lot different, and they don't emphasize on preliminary design. They directly reach ICD or the final design or final RFDS. How do they do that, and how they can do that, and why AT&T is not doing that? Uh, it's when you understand the whole process. By the end of the course, we will discuss this topic based on different operators in detail. Why different operators are doing different things differently. Okay. So that will be one of the main objective of our course, is to give you understanding of different approaches followed and different terminologies used in different operators and vendors as well. So till here, I tried to explain you how the course will work, what is inside the course, what will be the approach to our course, what is the design process is, and our course is basically based on radio network design process. Overall, we will be going step by step through the topics, detailed topics. Uh, and if you guys have any question, feel free to ask the questions. Okay, what was the stage channel capacity, spectrum fuse, sprinkles, etc.? Are they part of RFDS? Okay, in the design process, the capacity and the channel determination is done. Uh, Capacity is done at the time or before RFDS. What is the capacity requirements? Based on that, RFDS is determined, because capacity requirements affect the design itself and the RFDS. So capacity requirements and the channel requirements are determined in terms of RFDS, yes, before RFDS is prepared. The PCI or the PSC is usually planned after the RFDS is prepared. Ali Hatem, yeah, for sure. We'll be sharing a lot of training materials. We send you guys the prerequisites, and there will be a lot of training materials for you to come during the course. And there will be a lot of uh, tests at the end of each course. Even that at the end of this course, there is a around 50 or 60 question test, which you guys will be taking. We will discuss at the end of this session how you guys want to take the test. You guys want to take the test at your own time or the end of every class, so we can manage, but the test is already there, and there will be a lot of training materials which will be coming during the course. And between the breaks, or between the two sessions, you will have the training material and you will have the test to given online at your own time, at your own pace, but you'll have to complete it within the before the start of the next session. So we know the evaluation, what is the progress, what is the concern, and what is your understanding for each of the sessions. So at the end of this session, we'll have a test as well. Okay, so let's go to some of the RF basics of the course. Why I included this in RF basics, because for many of you guys it will be very easy things you guys already know. Many of you guys it will be new. So the reason I put it in there is to bridge that gap between the students or the audience of this course, that everybody understands what we will be learning in the other sessions of this course. So rest of this course will cover the basics. It's very important because it gives you very good insights of how the macro sites and the DAS sites looks like, what are the basic technological consideration do we consider, and what are the terminologies we have. For a few of you guys, maybe you already know, but for those who don't, it's very important. Especially, there will be a lot of things which any of you guys probably don't know if they are not already in the field. Okay, so we have again discussed that there is a nominal phase before the design preliminary phase, which is used for budgeting, or the RFQ, or RFQ is request for quotations, or request for proposal is RFP. If you start working on that domain, which is a higher domain of budgeting and preparation, or RFP or RFQ, you can at the end of this course, if you know what is the consideration in that part of the design, which is before usually, then those consideration is passed on to the markets, or the to prepare the final RFDSs. The thing is, this budgeting, RFP, RFQs, or nominal design is done at a higher level. But as an RF engineer, we should have a good understanding. But there are very experienced engineer you'll find working at that usually national level in those fields. The reason being for that is it requires a lot of understanding of how the things are done in the field before you can reach that level and prepare the budget to reflect the actual cost of any network deployment, and evaluate different quotations from different vendors and all of those things. And basically, once that is done, that is sent to the markets, which comes for us to prepare a preliminary design, which is PICD, and then the final design, which is ICD. Okay. So, but there are many inputs which is coming from there for your overall understanding that some of the things you will find in these organizations are part of the practice or already decided and they are being followed. Why is that? Because there is a lot of work which has been done centrally or at the national level for those practices to be adopted. And these practices keep changing as well, ongoing. But initially, when they are initially, let's say if a operator comes in, he has a UMTS network already, he wants to deploy LTE network, he will not just go in and start deploying LTE sites. He will come in and he'll see where he has to cover. So he will divide his plan in the phases, which cities he has to go, what coverage requirements he has, what kind of throughput he wants. Based on that, he will theoretically plan his network using, again, initially on a micro or Excel sheet. Then he will put those sites on a atoll and then see what is the coverage and to prepare for the budgeting or nominal design. Once they are finalized with the budget and they say, okay, we have that amount of money and that many sites we are going to deploy, we are comfortable with it, they request for quotations from different vendors. The vendors comes in, they say, okay, we will deploy the sites. They negotiate the pricing. Once the pricing is negotiated, they negotiate on the process, how they will deploy the site, how will be the design, and then they send that to their regional teams or the market teams. And then market teams say, okay, we have to deploy 1,000 sites. Big cities have more sites, small regions have smaller sites, number of sites. So that number of sites usually come in. That number of sites is variable within the range of 5 or 10%. That is already done centrally by the national team, and those number is being followed. So rest is basically implementation. For that, the number of sites are there, the ideal design or the nominal design is there. Then the market or the regional teams work on it to make a preliminary design, and that preliminary design, then they work again, as I was explaining in this process earlier. Remember, this process diagram is very important for you guys to understand in detail. So preliminary designs then is also done by the regional teams or market teams, and then they prepare initial RFDS, they put in and everything looks good, they put in the final RFDS. and that's how the things goes. But there are many considerations which are coming from the central team or the national teams. We should understand that. So we have to work in that scope of work which has been already been given, and the practices which already been adopted or communicated. So that's how the overall process works. The open end of the process was the central team, which I tried to explain the role of the central teams over here. I hope that's well explained. Are there any questions in this regard? You guys can type in. Okay, if you have questions, you can keep typing, and as soon as I see the question, I'll reply the question. In the meantime, I'll move to RF planning basics. Before we dive into the details of the planning, again, as I said, we will go into some basics. We have already sent the prerequisites of this course. Many of you guys were able to read it. Some of you don't. In any case, if you didn't read it, you can even read it after this session between now and the next session. So I expect you to go through all of it, every one of you, between now and the next session, and understand what's going on in that. Some of the basic concepts which are so basic that if you don't understand them, then you won't able to continue the next session. I have tried to explain over here, so we don't have any hoops or the gaps in the next session. So what are the basic concepts? So as we say, do you guys want a break for 5 minutes? Because after every hour, we should have a 5 minutes break. So we have reached 11. We'll have a 5 minutes break, or make it a 10 minutes. At 11:10, it's 11:02 already. At 11:10, we will come back. That is exactly after 8 minutes, we'll be back. So guys, I will be stopping the recording for that moment, and see you in 10 minutes. Go freshen up, grab a tea, and then come back. Thanks a lot. So yes, so what we were going through was our RF design basics. Now we'll be going through the basic concepts. Some of them will look like how the sites are, what are the micro and DAS sites, what is to give you a very good feeling before you jump in. So it's very easy for you guys to grasp the course material to come. So what is, for you guys who already know the concept of path loss, it sounds boring, but few of you guys, definitely it's a new concept. So we are talking about the RF engineering, right? RF engineering is a radio frequency. What is a radio frequency is? It's basically a electromagnetic signal. How it's generated? It's generated by an electrical signal. When electrical signal passes through any transponder, or transponder means anything which generate the form of a signal, or which is antenna. It passes through an antenna and it converts an electrical signal to an electromagnetic signal, and antenna also converts electromagnetic signal into an electrical signal. So basically, when antenna generates a signal, okay, we will go through the antenna concepts once. If you guys can see the material which I sent, I specifically sent you guys antenna theory document, which covers antenna. Because if you don't understand antenna and all those things, it will be really, it's a prerequisite of this course. So basically, whenever there is a signal, it has a loss. So it has a loss because of the distance between the transmitter and receiver, which is free space path loss, which is represented by this equation, which you can see over here. So this is a simple equation of free space path loss. Okay, one of the biggest challenges of RF design engineering is to predict a signal as accurately as possible. What will be the signal level at a given location away from node B or E node B tower? So that is a very big part, and that's why we use ATOL or planning tool like ATOL and Asset for macro sites or IDWave for DAS or in building sites. So this is one of our biggest challenge. So there are a lot of theoretical calculations which has been done. There are a lot of theoretical models which have been developed to predict. So one of the most basic thing which tells is a free space path loss is if your transmitter is in front of you and there is a straight line of sight, what will be the signal if you transmit 20 dBm? What will be how much signal you will receive at the receiver at a given distance is governed by this equation. Okay, uh, I will just explain you two things. You can see in this equation if the distance is higher, your loss will be higher. Okay, based on distance, and if your frequency is higher, your free space path loss will be higher. Okay, so remember those things. If the distance is higher, your free space path loss will be higher. If your frequency is higher, your free space path loss will be higher. Okay, so what it means is when you send a 20 dBm signal at the receiver, you will receive, let's say, minus 5 dBm or minus 8 dBm if your frequency is higher, distance is higher. So to give you a empirical sense that how it works, for example, if your distance is doubled, you will have a 3 dB higher loss. If your distance is half, you will have a 3 dB better signal. If your frequency is doubled, if your frequency is doubled, then you will have a 3 dB higher loss, free space path loss. If your frequency is halved, let's say if you are transmitting a signal at 800 megahertz, you have for example, you have a loss of 20 dBm. At 1600 megahertz, you will have a loss of 3 dBm higher. 20, you will have a loss of 23 dBm. The question was why 92.45? Then again, you will have to go how this equation is derived. So if you have been doing, how this equation has been derived, then you can only understand why it's 92.45. It's complete. If you know how different calculation like the Newton theory of gravity equation is derived, all those details are like what is actually okay. How I can explain? Okay, I'll be able to explain in next slides, I believe, more this concept. Even better, but that's a mathematical equation which governs it. What is propagation? So the signal transmits from transmitter to receiver. Another situation. No, this equation is not valid for non-line of sight, and that is what is our challenge is. If it is line of sight, then we can predict the signal strength more accurately. But in our environment of RF engineering, there is hardly any time line of sight between the mobile station or the BTS or node B and the UE or the cell phone. So that's the biggest challenge, and that's what we will understand in the next slides to come. So we don't have a line of sight, so the signal reaches us as a free space path loss. If we are standing in front, the signal reaches us as a reflection, as a diffraction, as a shadowing. So signal, before it reaches from the transmitter to our cell phone, it goes through different phenomena. Okay, And what signal strength will we receive is it's very difficult to predict. And that's why these planning tools are so popular, like Etoll or Asset. And not only you'll find these planning tools are very popular, you will see that these planning tools have different propagation models. And there are companies which have and their job is to make a more accurate propagation model and sell it to the operators, and the operators run those propagation model, test them, and see how accurately they are predicting the signal level in their different environments, and how to use them. One thing more which is very important is uh, one thing more which is very important we should all understand is uh, propagation is overall, it includes free space path loss, it includes diffraction, reflection, and everything. So we need something which does not only cover a tool which does not only predict based on the free space path loss, but also other phenomena of radio propagation, which are reflection, diffraction, and others. Like uh, like I'll go jump to this slide, then I'll go back. So you see, this is a base station, this is a UE. What we have is a direct side. There is a diffraction, which you can see. Okay, let me check. So you can see there is a direct line of sight. There is a diffraction, right? And also there is a reflection. So all these phenomena are called propagation. In general, all these phenomena which through which signal is received from a transmitter or base station to the UE, it's called propagation. And all the different paths it receives is called multipath. So a signal is propagating from transmitter to the UE uh, on multipaths, and this phenomena itself is called propagation of a signal. Okay, propagation of a signal from a base station to the UE. Does any of you have any questions or so far? Feel free to type it in. Multipath fading. Okay, now what is multipath fading? It's not fading. Fading is basically happens when this is multipath. Now, if the signal at the receiver make do a constructive interference, it will gain. If it is a destructive interference, then destructive summation, then the signal will fade. So it can fade, it can enhance itself. Uh, Usually the effect is 3 to 6 dB because of multipath in the propagation model, and the propagation model have to predict it more accurately. Signal can diffract. Okay. I got two more questions over here. Signal can diffract or reflect from any material? Yeah. But based on the nature of the material, the amount of signal which is diffracted or reflected will be different, but signal can diffract or reflect from any material. For example, water is considered to be a very, very good reflector. If you are throwing a signal on a water, you can see that signal somewhere like 50 or 60 miles away sometimes as well. And that has been experienced. So the sites which are planned across near the water, they are tried to be captured, especially in Manhattan, where the Bay Area, it's very difficult to control the sites because the sites start to uh, uh, overreach on the other side because water is a very good reflector. Is there refraction phenomena occurs? Refraction is a phenomena as well. Yeah. But usually refraction does change the path of light. The refraction happens when it starts are different, when signal is traveling through a medium which has different densities at different portions. Usually in the atmosphere, that's not the case. So refraction is the phenomena, but I don't think so in a propagation model it has a very big impact. but good propagation model, because learning a propagation model and theories and what are different propagation models, it's a science in itself. If I let you guys know, water bodies is between ms and node b, is there refraction phenomena occur if the water bodies is between, well, refraction, if it will, reflection will occur from the water bodies and node b. Refraction, water will, the signal will go inside the water, yes, but if the signal goes inside the water, it's means it's a lost signal. So there is a portion of the power of the signal. It's not a complete signal. We always mean signal means a portion of the signal will go as a result of a refraction inside the water, and some of it will be reflected out. The one as a, because of the phenomena of refraction, because water is a different medium and air is a different medium, and when it hits the water, some of it will be refracted inside the water and some of it will be reflected outside it. So the one which will go outside will go back to the atmosphere, and the portion which will be go inside the water will be lost anyways, that portion of the energy of the signal, because remember, it's energy of the signal we are talking about. Complete signal is never lost, is not lost. It's the energy of the signal is lost when it hits the water, because some goes inside the water and some is reflected by the water. So, and how much is refracted inside the water? I don't know. We'll have to go through some studies to do it. But most of the energy is reflected by the water, because water is a very good reflector. How much is refracted? It's less, because the studies and my personal experience, or everybody's experience will tell one thing, that water is a very good reflector. If you throw a if you're throwing a signal or your antenna is pointing towards water, then if water is continued for 50 miles, maybe you will able to see that signal after 50 miles because of the good reflective nature of the water. Uh, so now going back to the, so we understand what is a propagation is. Propagation is basically we should able to predict the, so is how the signal is transmitting from the base station to the UE, but how this signal is combined and what will be the receive signal level, then there is a lot of theories around it. Okay, there is a lot of theoretical models which try to predict the signal level, if it is transmitted from a base station, what will be the signal level at the UE. There are multiple base stations around each other in neighbor vicinity of each other, so what will be the signal level from each of the base stations. There is a lot of theoretical work which is being done, and it is a work in progress till today, because you will find like AT&T have a project which is called suburban project or rural project. What basically it's doing, they bought a new the propagation model. That propagation model was integrated with their planning tool, which is ATOL or ASSET, and they use that propagation model to predict the signal level more accurately inside. Yeah. So those propagation models, what they basically do, if you understand the radio propagation environment, you will find that there is a terrain or terrain, how you pronounce it, is like hilly, or the land is going up and going down. How is the terrain? Is it a flat terrain? Is it a hilly? Is it a mountainous? There is one thing. Then on the top of it is a natural vegetation. It has a trees, it has a grass, it is land, and over that there is a man-made structures which is called clutter. Okay, so there is terrain, then there was vegetation, there's a man-made structure, and overall all these three things makes a clutter. Okay, so what is our clutter basically? Urban environment has a different clutter because there are more man-made structure. Rural is a different, suburban is different. So you should understand there are different clutters. It's a rural, urban, suburban. So whenever you say a propagation model, you will also see a thing called tuning. You are tuning your propagation model. So most of the propagation models needs tuning. Means at least all of the ones I know. So there are at least tens or over 50 propagation model, but we will just discuss two of them, which are the most popular of them, and they are very basic propagation models. So there are very advanced level of propagation models. If you guys want, you can go and study. But so each propagation model is tuned. Tuned, what's tuning means that it every propagation models take some inputs to predict the signal. That those inputs depend upon the terrain, vegetation, and the man-made structures, buildings, homes, skyscrapers. That's called clutter. So each propagation model is tuned according to its clutter. Okay, so there are urban clutter, there are suburban clutter, there's rural clutter, all those things. So so it is tuned according to that. So what is clutter? Clutter is basically the environment in which the signal is being transmitted and received. Is it a urban environment? Is it a suburban environment? Is it a rural environment? Is it a dense urban environment? So these are the basic general classification of clutters: urban, rural, suburban, dense urban. You will also see hilly clutter tuning as well. So you can classify according to the needs, special needs, icy or Arctic clutter as well. You will find it like if there is ice everywhere in a mountainous area, there is ice, or it's a plain land like Antarctica, or it has ice. It needs to have its own propagation model according to that. It needs, no, sorry, let me correct myself. It has a propagation model, but that propagation model has to be tuned according to that clutter. So there can be many propagation models, but every propagation model is tuned according to that clutter. Some of the propagation models are designed for specific clutter like urban or suburban itself. So some of propagation models are designed for a particular clutter, but many of the propagation models are tuned for that specific clutter. Model tuning is a subject. You'll find the jobs of model tuning itself, RF engineers doing the model tuning. All those things comes before the network deployment usually. We will discuss it, some of it later, some of it further. But let's jump to where we were before. Uh, so we understand the propagation model better now. So what are the basic propagation models we have? So the ABC of propagation models start with Okumura model, Okumura Hata and Cost Hata model. What is Okumura Hata? In this slide you are missing Okumura Hata. It's basically complete name is Okumura Hata model, and there is a Cost Hata model, which is a combination of Okumura Hata model and another Cost model. It's this Cost Hata model is also called Cost 3 to 1. As I said, uh, companies and people develop their own models, which it's a very subjective study that which model is better than which ones. But Okumura Hata and Cost Hata models are one of the two very basic models. How they do it, basically, they have two equations, one for Okumura Hata, and there is a Cost Hata model. It's also called Cost 3 to 1, as far as I can recall. It also has a equation, and in that equations there are some constants like K1, K2, K3. And what you do, you go in the field, drive around, and sample the data, and predict what can be the K, and calculate the K1 values for different samples, and then sum it up what can be the K1 or K2 values. Maybe we can do a session later on this in more detail, but trust me, from the job perspective, which this training is focused on, it's very yeah, well, these two models, I believe they are no more used, because in last 3 or 4 years, there are many companies which have popped up, which have bring in their own model, which are more accurate. Cost Hata model and Okumura Hata model. neither T-Mobile nor AT&T is using them. What model they are using, we can discuss. But as an RF engineer, if you go in the field of the current job market bulk, or where the bulk of the jobs are available, the model is already set. You just have to select the model. That's it. That you are using this model, and that's again done at the national level. So everybody cannot use their own model for a given clutter type. You are directed to use a particular model. If the company decides to buy a new model, integrate it with their planning tool, run it, test it, and if they find the results better than the other model, previous model, they leave the other model, they use the new model, and they start direct their regional teams or markets team to use that model. So it's again done at the mostly then from the organizational perspective at the national level. But you guys should have the understanding of why it's being done and how it's being done. Uh, but if you have to do it, it's a very subjective study, and different companies are selling their own model. Maybe one day, if any of you have interest, can develop a better model than any other company and make a lot of money out of it. Do you mean we need to survey sites? Okay, there is another question. Do you mean we need to just go and survey sites, get K parameter and plug in into the company specific model? No, you don't have to survey the site to get the K parameters. Basically, you set up the test transmitters and then you collect the data in that clutter. So that clutter has its own behavior. So then when you collect the K parameters, you put in the Akumura Hata model or COS21, and then you calculate the values of K1, K2. So let's say you said first, before that, you have to classify. Yes, that's a CW testing. That's a continuous wave testing. This model tuning or propagation modeling is also called CW testing or continuous wave testing as well. So before that, you go, before you decide to tune a clutter, you have to go and identify your clutter. You define your clutter on the map. This clutter I will identify as a dense urban. This is urban. This is suburban. This is rural. Okay. So you identify, first classify your clutter, then you set up the transmitter for each clutter. Usually, ideally, that's the case. That's not necessary because the computer can differentiate between the boundaries of the clutter. And then you, based on the signal, how much losses were there, how much losses were recorded, how much losses were calculated, you calculate the K values for that clutter and put it in there. And then based on that K values, you are able to see. I won't go into any further detail because there are companies working on these theories. So it will be another discussion. I would definitely recommend you guys, for your own interest sake, go and study it. But I don't think so we need to go any further in this concept because it will take a lot of time and it's not aligned with the objective of this training course, which is to get the best body of the knowledge to get a job in the current market. Okay. If I that path loss equation which I explained you guys, if you draw it on the graph, it will look like something like this. You on y is a loss and x is a distance, and you see loss for 5300 megahertz and 2400 megahertz. You see 5300 megahertz signal has higher losses for the same amount of distance. For example, at 10 kilometer, it has a loss of 120 dB, and 5300 signal at the same distance has a loss of around 125 dB. So similarly, you can see from here that over here is 10 kilometer around 122, and over here it's like maybe 127, 128 dBm loss for 5300 megahertz signal. So this is another path loss, distance, and kilometer example, A and B. Now, the thing is, what you do is you predict the path loss. That was for free space. So simple equation which I showed you guys over here. over here, this equation, this graph, uh, this graph represent that equation, and over here, this is some of the propagation models A, B, C, and they are being compared. What is their prediction for different path losses? So it's just a theoretical calculation for different propagation models, just for idea how do we evaluate propagation model. Coming back to our, which we discussed this in detail already, that how we sum up our clutter and how clutter affects how the signal is reaching the UE itself. Okay, so there is an example of if you go to a planning tool and run a propagation, how the propagation for a single site would look like. I'm not naming any planning tool over here. What will we, when we'll go to the planning tool stage and when we'll be studying the planning tool, how to configure the planning tool, how to run the propagation in the planning tool, then that will be a tool. Over here, this slide is not from a tool. So if you have a single transmitter, if you have a propagation model, you can see what this propagation model is basically doing. You used a propagation model. I'm not naming even the propagation model we are using. We are using a XYZ propagation model. And this is a plain terrain. We ran the propagation. This is our transmitter in the center. And there's a signal which is spreading. We can see what is the propagation model basically doing. Propagation model is predicting signal at different distances. You move farther, the signal is going weaker. How do you know? There is a legend on the left. It says blue is -10, so it's going in the ranges of -10. If we are closest to the side, you see the very good signal of -70 and -74 dBm. For you guys who are working in the RF field, you have a very good understanding. We always talk about the signal in minus because dBm. Yeah, because dBm is a logarithmic scale. It's when you have power like 10 watt, 10 milliwatts received at a signal, which is a very small power, but a radio receiver can sense that power and that sense that signal. So it's -70 dBm. It's considered to be a good range of signal power for UMTS signal. I'm not talking about any other signal. For UMTS, there is a RSCP. We will explain the concept. What is the different RSCP, RSRI, RSSI? So this, I'm just talking about the concept of propagation over here. So the farther we go, the weaker the signal becomes, and that is the basically very basic ABC of propagation. What does the propagation does is this. Now, okay. So if we have a planning tool and we have a site, how the propagation would look like. We have more 3-sector site. We know every site has a sector. So we have a 3-sector site. We have a propagation. We are doing the how would the propagation would look like. You guys will see in detail when we learn the propagation planning tool, which will be a tool. But this slide is meant to give you a good feeling of how it's done and how it looked like before we reach there. So there are many sites over here. There are 7 sites. Each site has 3 sectors, and each site has been planned to radiate a signal. There's a certain power settings. How this has been set up, we will study. But that's how the propagation looks like. It gives us the range of the signal power, signal strength received at the receiver. So what this propagation model is telling me like if I am standing over here, I will get a signal. If I'm in yellow zone, I'll get a signal of better than -50 dB, -60 dB. If I'm in red zone, it's better than -60 dB. Yellow zone is better than -50 dB. If I'm in blue zone, it's better than -70 dB. M. Don't forget dBm. And difference between dB and dBm, very important. It's dBm, -70 dBm in the blue zone. And if you're standing in the green zone, it says it's between -70 and -80 dBm. Green zone is somewhere here, blue zone is here, red, and yellow zone. So that's what is the job of propagation model. Is it the only job? No. Does it only do that thing? No. Because I'm telling you the signal strength. With the planning tools which we have, they also tell you the quality. Quality means for UMTS, it is ECO or I naught. It tells you what ECO or I naught you should expect in a given zone. It gives you a similar plots for ECO or I naught. For LTE, it's SINAR. It gives you similar plots for SINAR. Or in LTE, we also use SINAR or RSRQ. We will discuss that in the slides to come. They also predict that not only signal strength, it also gives you the throughput you should expect or at those locations based on different simulations, which again is an advanced level of simulation, but the concept behind them is the same, but the logic or the mathematics used behind them is different. We will learn those simulation. For example, to simulate a UMTS network or LTE network, it also depends what is the distribution of the user. So the coverage changes with the distribution of the user. There are many users very far, then there will be different coverage. If the users are very close, there will be a different coverage. There will be different quality, and there will be different throughputs. So there is a simulation called Monte Carlo simulation, which predicts based on the user distribution, it predicts the coverage. It predicts the quality, and it predicts the capacity or the throughput. So remember these three words. For an RF engineer, these three are very important things: coverage, quality, and throughputs or the capacity. Throughput or capacity usually are considered the same thing. Coverage, quality, and the capacity. In technologies changes, the way we measure these coverage, quality, and capacity changes, the jargon changes, but the coverage, quality, and capacity measurement techniques, their analysis techniques always remain the same. So in UMTS, for coverage, we have different parameters. For LTE, we have different parameters, and we will be discussing it in these slides. For example, how do we measure coverage and quality in UMTS? For many of you guys, you already know. For few of guys, you don't know. But in UMTS, coverage is based on power transmitted by the pilot channel. And what we measure, the UE always measures and makes its decision for handover and other things based on coverage. And the coverage parameter of UMTS, which it measures, because one thing, it can have many different parameters using which you can predict coverage, like RSSI, RSCP, or something else as well. But what is used by the system to make decisions for handover, quality, and coverage? It's called, in UMTS, it's called RSCP. RSCP is received signal chip power. Well, what is received signal chip power? That was the basic reason. It's basically identifies what is the power you're receiving on your pilot channel. In simple words, what is your reference signal or the beacon signal? What is the signal strength of your beacon signal? That's what it's telling you. And based on your beacon signal, it determines what is the coverage you are having. How much do we power? So we have a power, okay? The power is, let's say, 40 watts. 40 watts comes to about 43 dBm. I'm not sure. We can calculate. So 40 watts. So 40 watts power. Then what we do, we say, okay, for 40 watts power, there will be power for pilot and the power for other traffic and other. So we in UMTS, as a rule of thumb, 10% is minimum allocation for pilot power. So which is for 40 watts, 10% will be 4 dBm. If 40 watts is 43 dBm, then it will be 10 dB less, which will be 33 dBm. I'm not sure 40 watts is 43 dBm, but let's assume 40 watts in logarithmic scale is 43 dBm. So that's how, but you should remember what is RSCP. In UMTS, signal quality of the signal is measured using RSCP. RSCP is measured against each cell. each cell is identified by two things. One is called cell ID and the other is called scrambling code. So when you see a cell in, you will able to see, you want to see the signal strength, you will able to see the signal strength, which will be RSCP. What is the strength which the system measures? Because there is another thing called RSSI. RSSI is the combined signal of all the cells receive a combined signal of all the transmitting signals. Because remember, we are talking about a cellular network. Okay, I'm going back to this slide. We are talking about the cellular network, right? In cellular network, if UE is at a given spot over here, let's say, then it's receiving the signal from all these uh, uh, from all these base stations, because all these base stations are transmitting at the same frequency. Since they are transmitting at the same frequency, if the UE is sitting over here where my cursor is or the pointer is, then it will receive the signal from all this from all this one, this one, this one, this one, if the UE is over here where the pointer is. So how to differentiate between the signal? If you start to measure RSSI, then this is the addition of all the signal, all the signal received by all these base stations. Maybe some of the signal from this base station is reaching over here as well. So RSSI cannot be the measure to make decisions if you want to camp on the cell. There should be a specific parameter or thing which identifies the power from that particular cell, not the base station, the cell itself. So that thing in UMTS, it's called scrambling code, and the RSCP is measured against each scrambling code to identify what is the strength and should we hand over from this cell to this cell, or what is the quality of this cell. So the strength, the quality, and everything is measured for the pilot channel, and it's measured against the cell. And for signal strength, it's called RSCP in UMTS, and that's why it's used. Do you guys have any questions regarding this RSCP concept and RSSI concept? So you mean RNC will measure RSCP of PSC? The thing is, RNC, it's measured by the UE. UE will measure the RSCP of a PSC. Yes, and UE will report that RSCP of that PSC in the measurement reports to the RNC. It will go to the node B, and then it will go to the RNC in case of UMTS. In case of LTE, it will only go to the E node B. So yes, those decisions are made by based on RSCP, but the measurements are done by the UE in the downlink and node B in the uplink. So you guys should have a good concept of downlink and uplink. What are the levels of RSCP of good? Okay, yeah, there is a rule of thumb for RSCP. Any RSCP better than -70 is considered good. Between -70 and -90 is considered okay, and anything less than -90 and -100 is considered bad, and -90 and -110 is very bad. After -110, there is considered to be no signal if it's more than -110. But network are designed for a desired. You remember we were discussing what are the desired criteria. So that's a very good question to answer that question. Desired criteria, we say, okay, the rule of thumb says signal level should be, we are designing a network for a minimum signal level. So what should be the minimum signal level? An operator says, okay, for me -100 is fine. The other operator says, no, -95 is fine. So there is a UMTS 3GPP standard, which I believe states -112 or -110 to be the minimum signal level. After that, you should not expect a coverage of UMTS. But operators don't design their network on the minimum. They come in and they say, okay, for me, the minimum coverage is -95 dBm for RSCP, because below that, I cannot assure the coverage because I want to design my network for a given KPIs. In order to assure those KPIs, you have to reach the thresholds of coverage and quality. In UMTS, the threshold for coverage comes from RSCP. In LTE, the coverage threshold of coverage comes from RSCP, and the quality in UMTS comes from EC or I naught. So operator says, okay, my network is designed for EC or I naught of -10, but the 3GPP standard states you can have a voice call at -14. Voice call, not data call. I'm talking about at -14 dB of EC or I naught. Okay, so that's what 3GPP states, but operator says, oh, no, I want my network at -10. So that's in order to have a good quality network. So remember, this coverage and quality relates to yeah, I'll explain in EC or I naught RCP in a bit more detail in the slides to come. So so we should understand this coverage and quality are related to the performance of the network, or the KPIs. KPIs are key performance indicator. Note it down. Key performance indicator, KPIs of the network. So these are all interrelated. So RSCP, I explained you, is the signal coming from the UMTS transmitter. Out of that signal, some of the power is given to the pilot channel. That pilot channel signal, the UEs or the cell phones measure that pilot channel in the UMTS and report it back to the node B, A, and the RNC. This is called receive signal code power. This is the measurement of how well the signal is good or bad. I just explained you guys the rule of thumb that anything -70 or better is considered good in UMTS. -70 and -90 is okay. -90 and -100 is bad, and anything -100 and below is very bad. So based on that, it makes the threshold and the parameters are set, which is a part of optimization. How those parameters are set. This is a design course, so we will not go there in the optimization details. Optimization is a separate course, and it's a very lengthy course as well. It cannot be covered. All the things cannot be covered within the sphere of this discussion. So once we know what is our signal for UMTS, we have to measure the quality, because I said three things are important: coverage, coverage, quality, and capacity. Because your capacity depends on the quality heavily. In the next session, I'll explain you the capacity concepts before we dive into the designing. So just understand it's RSCP for UMTS. It's a pilot beacon power channel. It's measured against each scrambling code or primary scrambling code, and it is the basically broadcast channel for each UMTS cell. Okay, and UMTS cell is identified by two things: its cell identity and its primary scrambling code. And that's because why we have so much identities attached to a cell. The reason being, when you are moving with your cell phone, how your cell phone knows which cell it's talking to. So cell phone identifies the node B and which cell of the node B, because each node B has many carriers, many cells. So we'll explain the concept of carriers and cells in the slides to come. The node B identifies cell using its cell identity and its scrambling code, basically, and it reports the quality and the signal strength measurements to the RNC or the node B based on that cell identity and the PSC. Node B itself is a node which has can have one cell, can have more than one cells, or can have one sector, can have more than one sectors. We will explain that concept in slides to come. That's why I said for many guys this is boring, which have already been there. For few guys, this will be new thing. So I have tried to bridge that gap in this first session. Okay, so staying at the UMTS. In UMTS, the quality is measured by, there are three things: coverage, quality, capacity. We are discussing coverage and quality over here. We explained how the coverage is measured in UMTS. Now we will see how the quality is measured in UMTS. It is measured by the quality of that same power channel. A signal of RSCP, which is the pilot channel, it has a signal strength. It also has a quality associated with it. So when the UE measured its quality as well. And the UE measured its quality in terms of EC over I naught. EC over I naught basically mathematically is the signal strength minus the RSSI. That's a most simplified mathematical definition of EC over I naught is. Okay. So what it does, remember, always whenever you talk about quality, there is a signal power divided by the noise, signal power divided by the interference. Okay, so interference is composed of two. There is an interference for a cellular network. Interference comes from two sources basically. Once from the other cells, because we in UMTS and LTE, unlike GSM, which we are not discussing here, in UMTS and LTE, the cells are transmitting, there are many cells are transmitting at the same frequency, okay, unless you add the carrier which transmit at a different frequency. So all the cells which are using the same frequency, has the same UARFCN, will interfere with it, with the UE. So interference, so you have a signal coming from, let's take this one. Okay, you have a you are sitting over here. Okay, you are sitting over here. Okay, let me put up the pen. Okay, your mobile phone is here. Okay, you are connected with this cell. Okay, now you have signal coming from this cell as well, because it's transmitting at the same frequency. This as well, this as well. Maybe some of the signals from this is also reaching over here. So this is your signal. Where is your signal? Your signal basically is, this is your signal only. This is your signal. But all this is this, and this is interference. Okay. So what is UE is, for this UE, ideally it wants to hear only this signal, but it's getting interference from everywhere, from here, from here, from here. So these are node Bs. Each node B over here has 3 sector. Okay, this is a node B, it has 3 sector. Okay, each sector, let's assume, we don't know, but let's assume it has only one cell. Okay, it can have more than one cell, and it has only one carrier. So let's say it has only one carrier. So each node B has one carrier. They are interfering with each other. It can be UMTS, it can be LTE. In both the cases, the phenomena remains same. So the UE is connected with this cell, and it is getting interference from all of these. So it's a, how will UE measure its quality? In case it will divide the signal of this. This is called carrier signal. Usually we use the word carrier for this. This is called carrier signal divided by the signal strength of all of this cells, all the interference received from this. So this is interference. Okay. But there is a problem with the UE. So UE, when it's measuring, it's hard for UE to differentiate between the signal strength from this or the other. So the signal strength of this is also added into the interference. So there is two interference basically. One is the system interference. When we are measuring the interference, there are two interferences. One is what we discuss over here is a carrier, which is coming from the cell which is UE is connected with, and there is interference, which is system interference. So far we discussed only, okay, which is coming within the system, within these base stations. This, all these are or intracell or intercell interference. Yeah, you can say that this is intracell interference as well. That's a terminology we will come to know. This is the intracell interference, or intracell interference is more accurate word. Plus, uh, plus we have over there thermal noise. So this is thermal. So thermal noise, go. This is your assignment for one of the assignment. Study thermal noise in RF engineering. Thermal noise. So our quality of our signal is determined by our carrier signal. Then we divide the power of our carrier signal with our intercell interference or plus the thermal noise. So this is our total. That's how the quality of our signal is determined. I hope. So what is thermal noise? I won't go into the detail. You guys have to go and study those details yourself. And maybe I included in the next quiz, because we'll have a quiz for this session. We'll have the quiz for other session as well. So I can include it. No, multipath fading is not interference. If the signal is coming from, let's assume, as long the signal is coming from, let's go back. If the signal, we have this over here, right? This is our mobile phone. This is the desired signal. So desired signal is coming from here, and desired signal is coming after reflection from here. Desired signal is coming from after diffraction from here. Let's assume that. Okay. So signal is coming from these three sources. All these signals are not interfering with each other. Okay. The interference will only be caused by these signals, which are intercell signals, which are transmitting at the same frequency. So this is not causing interference. This can increase the signal strength. This can decrease the signal strength based on constructive destructive interference. Usually it increases, multipath increases the signal strength usually, if we are not going through the phenomenon of multipath fading. Also note, go and study multipath fading. So that is your assignment as well. Note it down. Go and study multipath fading in RF engineering. So this is one of your guys' assignment as well. So no, multipath will not cause interference. It can decrease the strength, but it will not be an interferer as such. Okay. Would rake receiver concept be used in this case? UMTS utilizes rake receiver, yes, and rake receiver is used to differentiate the signal strength. So rake receiver, when we go through the UMTS itself, we'll discuss rake receiver in superficial details in the next session. As far as I recall, yeah, it's the next session. Yeah, but rake receiver are used in UMTS, and let's make an assignment as well. Study rake receiver in UMTS. Okay, what was the question? Let me study that. There is a question from Khalil. Intracell have different frequencies. Do they cause also interference? Intracell have different. No, intracell. If you're saying intracell interference in UMTS and LTE, when we talk about intracell, it's supposed to have same frequencies. So whenever it's on the same frequencies, it will cause interference. If it's on different frequencies, which are called carriers, if it's a different carrier, it will not interfere with that cell. But if it has a same frequency, it's an intracell. Then if it's an intracell neighbor, it means whenever you say in LTE or UMTS, if it's an intracell neighbor, note it down. If it's an intracell neighbor, then it means it has the same frequency, which means it has the same uplink UARFCN and downlink UARFCNs. Okay, and it will cause interference if it is in the vicinity of the cell. But if it's a different carrier, it has different UARFCNs, then it's a different frequency. Now I'll move to the quality, the coverage and the quality concepts for LTE. So far, do we have any questions regarding quality and coverage? I know there can be a lot of questions, but any relevant questions you can ask me before I move to coverage and quality measurements in UMTS. Sorry, in LT. No, RSCP represents coverage. ECORI not represents quality in UMTS. Okay. Okay. Now let's go to LTE. Now in LTE, coverage is measured by RSRP. Well, what is the difference of RSCP, RSRP? Well, there is a big difference, but conceptually they are used for the same purpose. So in different technologies, in remember in UMTS it was a pilot channel. Over here it's also a signal from the pilot channel. It's not the power for the whole cell. So if it's like a 40 watt, it may be 5 watts or 8 watts, but it's usually the power allocated out of the whole power for LTE is less than the UMTS, number one. Number two, remember that, note it down. The pilot channel or the pilot channel power in UMTS is configurable. The RF engineer goes and calculate and configure it themselves. Have you guys noted it down? It is very important. In LTE, the pilot channel, which is called reference channel. In LTE, it's called reference channel, and it's measured using reference signal radio power, RSRP, reference signal radio power. This power is basically reference signal radio power is it comes from the pilot channel and the pilot power of LTE cell or the LTE transmitter, but this power is not configurable like UMTS. It is fixed by the vendor based on some calculations which we are not discussing over here. But it is fixed. It's not configurable by the RF engineer. In UMTS, seepage power, it's called seepage power, or the pilot power is configured by the RF engineer. RF engineer does those calculations. And as a thumb of rule, in UMTS, it is 10% of the total transmitter power, okay, or total cell power. Okay. So moving on to LTE, in LTE coverage is measured by RSRP, reference signal radio power. Whenever we are talking about the signal strength, the unit of the measurement will remain same. It is dBm on the logarithmic scale. It's watt on the linear scale. You guys should understand what is logarithmic scale and a linear scale. If you guys already do, excellent. If you guys don't do, write it down as your assignment. Logarithmic scale, what is logarithmic scale, and what is linear scale? In RF engineering and electrical engineering, instead of using directly dealing with watts, we always use dBm, which is a measurement of power, and watts and dBm are interchangeable. You'll find online a lot of calculators, like 40 watts is how much dBm and 43 dBm is how much watts. You can calculate it interchangeably. There's a mathematical formula, and there are a lot of calculators which do it for you, and many of them are available online. There are a lot of tables as well. So in UMTS, RSRP, which is again like RSCP, is measured in dBm, gives us the coverage. It's a pilot channel power. What is the rule of thumb of good coverage for RSCP? I would say a rule of thumb. It's not accurate. Don't quote me, but whatever it's for UMTS, it's 10 dB less for LTE. Okay. I got a question I missed out. So the more ECRI is, the better quality it is. Yes, the more ECRI not, the better quality it is. Yes, and better the signal strength, the stronger it is. Yes, but remember, ECRI not ranges usually, and the signal strength RSRP and RSCP ranges are in negative. So mathematically, we all know that minus 70 is stronger than minus 80 because it's minus 80 is smaller than minus 70 mathematically. So just to explain you guys. Okay, so far we said RSRP we understand. So RSRP is used to measure signal coverage in LTE. How do we measure quality? So in LTE, the quality in LTE is measured using two different quantities. One is called RSRQ, which is reference signal radio quality. Okay, RSRQ, how it's measured is again RSRP minus RSSI. So you see the similarities between their mathematical calculations, right? If you guys can recall, how what was the calculation saying? Sorry guys, I'm missing my slides. Okay, okay. So if you guys can recall this equation and the equation before that, this is for LT, and the equation before that for UMTS, this equation. So pretty much over here, pretty much the way they are calculating the quality is similar. They're subtracting RSSI for UMTS and from RSCP, and for LTE they are subtracting RSSI again from RSRP. So this is a general way of calculation, and pretty much mathematically it's very similar. Guys should understand what is RSSI itself. What is RSSI? Well, you are standing in the middle. You have a lot of base station transmitting around you. You can receive the signal from all the base station. The combined signal strength on that frequency from all the base station is RSSI. Simple. Is there any question about RSSI right now? Or is it clear? Okay, sounds good. I'll move. So don't hesitate to type the question. All node B. Didn't understand all node B. So the more all cells. Whenever I say node B's, it means from all the cells of the node B's. So always remember, it's always the entity which UE can measure is not node B. Or UE connects is not node B. It is cell. So from all the cells. There is no as such optimal range for our RSSI, but there is optimal range for quality. So if mathematically you say RSSI is going higher, then definitely that our quality is going lower in both the cases. Okay, because you are subtracting RSSI from RSRP. As soon as you are subtracting it, RSSI, the value of RSRQ is going down, which means the quality of the signal is going down. We have the ranges for the quality. So if your RSSI is very high, because there are a lot of transmitters, you did not plan the network well, there are too many signals coming from too many base station at a place, then your RSSI will go up, which will affect your quality. Both for UMTS and LTE it is true, and as soon as your quality goes down, you will have ranges to meet your quality rule of thumb and standards to meet your quality. So for RSSI there is not as such any rule. In the downlink there is no rule. In the uplink we have some rules. We will discuss it later. Arshad Hussain, I did not understand. Okay, there are two questions. Could you support it with the scenario as you instructed well in the interference scenario? Okay. Okay, guys, we're running short of time. Okay. Let me go. I'll reply to Zahid's question first, and then I'll go to Arshad's question. Okay, we are sitting over here. Okay, this is our UE. Okay. All the signals, this is our desired signal. This is our signal which we are receiving anyways. So UE is receiving all the signals, right? So UE for it's all the signals. And for UE, based on the code power in WCDMA, it identifies the signal, separates the signal based on code power or the PSC, or the, you can say PSC based on the PSC. Theoretically, you can say that PSC. It identifies the signal, but it's on the same frequency it's receiving the signal. So the PSC it's measuring using RSCP, right? But how is it? But all the signals are receiving and are adding up. So it identified this cell and its signal strength using a quantity called RSCP, where it is carrier signal is coming from, or the connected where it is connected with is coming from. But all these are adding up. So all these is interference. So what is this? This is RSSI. Okay. So if you are on a logarithmic scale, you will minus RSSI out of it to get the signal. But remember, you should also include the thermal noise as well, which for the simplicity is not included, but thermal noise is part of the is part of the calculation for quality. So what will be your ECO or I naught for case of UMTS? It will be this. So, but what does this RSSI means? RSSI is addition of all of this interference plus carrier itself. Okay. So for you guys, you should understand one more thing. On logarithmic scale, instead of division, we subtract. So we are talking about logarithmic scale and we are subtracting. I hope that answers your questions, Ahid. Okay, I'll move to Arshad's question. I don't know what was his question first. Okay. Can you repeat RSSI one more time? No, it's good. Okay, Shayan says, no, it sounds good. Okay. Okay, so let's move on. And we got, no problem, Shayan. Thanks a lot for asking the right questions as well. Because if you guys ask the right questions, you will enrich the whole process, which is very excellent. So focus on the question. It was a very good question. You guys asked the right questions. It will be beneficial for all of us. Okay. So we understand the concept of quality, but one thing, there is a little trick or twist in LTE. In LTE, I told you the quality is measured by two quantities. One is RSRQ, another is SINR, signal to interference ratio. For one reason or the other, during their research or the later part of their research, they found instead of RSRQ, they should use SINR for the reporting purpose. So they started using SINR. SINR is, what is SINR? SINR is similar to RSRQ, but RSRQ is measured or reported on logarithmic scale, and it's little different than SINR because it does not consider thermal noise, as you can see in the equation. Because to measure the quality, thermal noise is important. In UMTS, ECO or I naught does consider thermal noise. In this equation, it has not been expressed for the sake of simplicity. Okay, but in UMTS, ECO or I naught contains the intra-cell interference plus the thermal noise, which is very important to consider. What do you say? For UMTS, RSRQ did not consider thermal noise, as far as I know. Maybe this is the reason they go to the SINR. Now, SINR is basically measured on linear scale. So when you talk about ECO or I naught, which is on logarithmic scale, or RSRQ, you will hear like -8 is a good SINR. -8 is a good RSRQ or ECO or I naught in case of UMTS, ECO or I naught. But when you talk about the linear scale, you don't talk about negative values like that. Usually the good value is 10 or above, or 12 or above, or 15 or above. Anything below 5 is considered bad when you're talking about linear scale. And SINR is a linear scale, is measured sorry, it's not measured on linear scale, but SINR is measured in dB. It's measured on logarithmic scale, but the good values for SINR are considered to be 10 or above. And SINR is basically, you will, in a whole of our discussion or practically in the field, you will hear SINR. You will hardly hear RSRQ being discussed for a signal. Okay. What is RSCP and RSRP? So there, we try to clarify the difference between RSCP and RSRP. First of all, they are used for two different technologies, but both are the pilot channels for the two different signals. RSRP is estimated over 15 kilohertz LTE subcarrier, while UMTS RSCP is measured 5 megahertz. So in UMTS, a carrier is 5 megahertz, always fixed. One carrier is 5 megahertz. In LTE, it can be 5, it can be 10, it can be 15, it can be 20, it can even be 1.4. Theoretically, it can be anything. Practically, the vendors have come up with 1.4, 5, 10, 15, and 20 megahertz of LTE carriers. But in UMTS, the carrier is always 5 megahertz. So 5 megahertz, when I say 5 megahertz, it means 5 megahertz in uplink and 5 megahertz in downlink, because we always deploy FDD channels. So you guys have third assignment, which is what is FDD channel, frequency division duplexing, and what is TDD, and what is LTE FDD, what is LTE TDD, what is UMTS FDD, and what is UMTS TDD. You will find that all of the networks which we have in the United States or Middle East or expected to be deployed in Pakistan, they are all UMTS FDD, frequency division duplexing. What is the basic difference is, in frequency division duplexing, you have a separate channel for the downlink and separate channel for the uplink, separate frequency bandwidth for uplink. So in UMTS, 5 megahertz for downlink, 5 megahertz for uplink. So totally this is 10 for UMTS, but we say that the carrier is 5 megahertz because in downlink it's 5 megahertz only, and in uplink it's 5 megahertz. But in total, the frequency being used is 10 megahertz. Same goes for LTE TDD. If the channel is, let's say, is 10 megahertz channel, then 10 mega, and it's LTE FDD, then there will be 10 megahertz in downlink and 10 megahertz in uplink. So remember that. This is very important. Duplexing is very important concept. It's a very basic. That's why I'm covering it in so hurry. So we will do FDD LTE planning totally, because that's what is being used. FDD is being utilized and deployed everywhere. TDD only we go where there's a shortage of a spectrum and we don't have a bandwidth for uplink. So what we do, we combine uplink and downlink both in the same channel, and we call it TDD. And TDD is deployed very few places, maybe very few places. Yes, I have never worked on TDD personally, neither UMTS nor LTE. Okay, nor I can recall where it has been deployed. Okay, is always weaker. Okay, so if you're deploying a network, this is a practical case scenario. So listen to me very carefully. If you are deploying a UMTS network, if there is a UMTS network and you come and deploy LTE network, and you say, okay, LTE RSCP is minus 80, and UMTS UMTS RSCP is minus 80, and LTE is minus 90. So it means it's the same thing. Okay. Because pilot channel power, for what we are measuring, we are not measuring the whole transmitter power. We are only measuring the pilot channel. So pilot channel for UMTS typically, not exactly, is 10%, which is typically comes to usually 33 dBm for a 40 watt radio, because most of the deployments are 40 watt, which is, I guess, is 43. So you will find it 33 dBm. For LTE, if it's a 40 watt radio, you will still see the power is not 10%, it's less than 10%, and usually it comes to about 23 dBm or 22.5 dBm for LTE. So wherever you go, you will see, if somebody asks you to compare, okay, over here UMTS coverage is minus 80 dBm, but LTE is minus 90. Yeah, it will be minus 90 because you are measuring RSRP in LTE and you are measuring RSCP in UMTS, and UMTS RSCP has usually 10 dB higher power than LTE RS. UMTS RSCP has 10 dB higher power than LTE RSRP, so that's why you will find it 10 dB stronger. So all the threshold, like what is the best coverage in UMTS, is minus 95 dBm of RSCP, but in LTE it is minus 105 dBm of RSRP. So same rule of thumbs. Yeah, you can say it's a similar rule of thumb, but there is a inherent difference of 10 dB, and this 10 dB is again a rule of thumb. It's not exact, but that's what you should expect. Okay, so I believe we have gone through RSCP, RSRP. We are coming towards the end of the session already, or we have 30 minutes more to go. Do you guys have any questions before I move to the next session? What parameters present throughput capacity in LTE UMTS like RSRP? Okay. What was the question? There is a question: what parameters represent throughput capacity in LTE UMTS like RSRP or coverage or RSRQ? Okay, throughput is not represented by throughput is measured in megabytes or megabytes per second or kilobytes per second or kilobits per second. So that's the unit of throughput. So how the capacity is measured, that will be in the next session. We have how to measure congestion and capacity and how to measure it and what are the factors. It's the next session which we'll discuss. But to answer the question, throughput is heavily dependent on quality. Okay, it's a direct function of quality. So if the quality goes down, your bit rate goes down, your throughput goes down, and your capacity goes down. So it's capacity or the throughput is a function of quality. In order to have a good network, we'll have to have a good signal strength. Good signal strength means we can have a good quality, good signal strength from the given signals. So good quality, and good quality means good throughput, less pilot pollution, less noise, less odd things, which we'll discuss how to reduce and how to design. So RSRQ and SINAR both refer to the quality of the LTE network. Yes, RSRQ and SINAR both refer to the quality of the radio network. Absolutely right. But in the network algorithms, we have seen that if you go to the optimization, you will see SINAR is being used in LTE and RSRQ. UE reports, I believe, UE reports RSRQ, but that RSRQ is again converted back into SINAR. There is a standard interchangeable. RSRQ and SINAR are interchangeable. You can convert SINAR into RSRQ and RSRQ into SINAR mathematically. So, but in calculation of the node Bs, all the algorithms which the node Bs or the radio network uses, they use SINAR in LTE, not RSRQ. Why? This is a different discussion. This is a theory how the network was evolved or the research was evolved. Any other questions before we move on? Okay. So one of the basic concepts which as an RF engineer, especially as an RF design engineer, we should all should know is very necessary is why we call it a cellular network. Cell looks like something hexagons, which you guys should able to see right now on your screens, right? So why should we call our network a cellular network? Okay, the reason being is in order to geographically calculate the coverage of each cell in a three-sector cell, the best method to calculate a coverage of a cell is using is considering it a hexagonal cell. You got my point? Did you guys? So theoretically, the best way to calculate the coverage of the cells, if the sites are three-sector sites and they have a given cell range, then to calculate the coverage, theoretically, it's a complete theoretical calculation. The coverage area is by considering cell as a hexagons, as the whole network is considered of hexagons. So theoretically means your human mind pushes us that, okay, if it's a hexagon, cell is at the center of the hexagon and it should be considered. Our node B should be at the center of hexagon. It should have 3 sectors. No. At the corner of each hexagon, there is a sector pointing towards the center of the hexagon. Center of a hexagon. You can see this pointing towards center of hexagon. So if in your cellular network, you consider your whole network as distributed in hexagons, equally sized hexagons, and each of your node B is pointing towards the center of the hexagon, then if you know the range or R of each sector, this is one sector. If you know the range of each of this sector, this sector, this sector, you know the R value, how far it is going, this is R, then you should able to calculate the coverage area for that sector. Means theoretically, that's a theoretical consideration, because this sector is covered by 1, 2, this hexagon practically would be covered by 3 cells, right? So theoretically, it will be covered by 3 cells. So 1, 2, 3. But mathematically, it's very accurate to consider it one cell, and to consider it one cell and to consider it as one cell and calculate the cell area based on this formula. So if your cell structure, your node B's are planned with the 3 sectors pointing towards the center of the hexagon, you can use this formula. This formula is basically area of hexagon, 2.6 R square. Don't ask me how it's derived. If you have done the geometry, you go to the geometry, you find the area of hexagon. In the geometry, there is a theorem which calculates the area of the hexagon, if you remember the geometrical theorems which we used to study sometimes back. So this formula comes from there, and it's very useful for when we use it at the stage of nominal calculations. It's a very important formula, not preliminary, nominal calculations. You guys should recall when I say nominal, what I'm talking about. If you don't, you guys were not attentive. You should be then. Okay, guys. Okay, so this is a theoretical calculation of cellular network. So let's see how our macrosites look like. So let's have a feeling of how macrosites look like before we jump into the session in our next slides. Remember, this is very important. Now, I said it has 3 sectors. Now, we look at a site. There are 2 different examples. One is a tower and one is a rooftop. Both are outdoor macro sites. Both are outdoor macro sites. So you see three faces. On each face, you see more than one antenna, 4 antennas. On the right diagram, you see around 4 antennas on each sector. Okay. Why 4? We will discuss that. There can be multiple different reasons. On this side, we see 2 antennas on this sector. We cannot see the other sectors because it's a building. We see 4 sectors. We see 4 antennas in one sector. We see 2 antennas. Basically, over here we see also 4 antennas, 2 small antennas and 2 big antennas. We also see 4 antennas. Why? Okay. Now there can be different considerations. What can be the consideration? Maybe this site has UMTS and LTE both, so it's using 2 for LTE, 2 for UMTS. But you know, the antennas can be shared between different sites, between UMTS and LTE as well. So maybe it was having like 8 feeder after combining and duplexing. What is combining and duplexing? We'll discuss it. If you don't know, if you don't, you should better, you will be able to understand what I'm saying. So after combining and duplexing, there were minimum 4 antennas. You didn't want to combine or duplex more because combining and duplexing has a loss up to 3 to 6 dB. You do not want it to introduce the loss, and that loss will come in both uplink and downlink. So especially for uplink, which is more power sensitive, you could not do that. So in the final design, as RF engineer, you decided I will have 4 antennas. You went to the construction team. Construction team said, okay, we can deploy 4 antennas to fulfill your requirement. 2 antenna will go to the UMTS, 2 antenna will go to the LTE, other one will go to the UMTS, one will go to the LTE, 2 will go to the GSM, whatever your site is. Remember, repeat, I'm saying a very important thing again. RFDS is per site. It's not per technology. Okay. So when you have a RFDS, you will have to consider other technologies as well in the same RFDS. Okay. So that is the important thing, that in case of RFDS, UMTS, LTE, and even the GSMs have the same RFDS. Okay. But when you go to the LTE, you can ignore it because it may not be important, or you can you should have some sort of information about the RFDS. But RFDS is considered to be per site, not per technology, whereas RND-CIQ is strictly per technology. Okay, so when you prepare RFDS, you will have to have a separate RND-CIQ for LTE and UMTS, but RFDS for LTE and UMTS will be same in most of the cases. So because the site construction teams is not very, they need to know what to deploy and how to deploy irrespective of the technology. They know what is LTE, they know what is UMTS, which cabinet belong to LTE, which cabinet belong to UMTS, which antenna is connecting to LTE, or maybe LTE and UMTS both are going to the same antenna. Maybe the antenna is a quad pole antenna. There are a lot of hundreds of consideration. For transmission diversity, we don't introduce. When we use more than one antenna, usually we configure it in a way that transmission diversity is already introduced in the network. So for to understand further all these things, you guys will have to go through complete detailed RFDS, how RFDS is designed, what is a 2C RFDS, if the site is, because number of antennas is depending on what thing. Let's understand the variables. We cannot understand the RFDS, let's understand the variables. It depending on if the site is only UMTS or it is UMTS, LTE or GSM as well, or only GSM or only LTE. Number one. Number two, if the site has 1 carrier or 2 carriers or 3 carriers or 4 carriers, number of antennas also depends on that. It also depends on if the antenna itself is a quad pole antenna. Maybe you cannot use quad pole antenna because it's bigger in size and the site does not allow, or the owner of the site does not allow you to install those antenna, or the structure cannot support heavier quad pole antennas, so you have to use more antennas, or there is a load distribution in the structure, there is a frame, so the structural engineer, the civil engineer, or the construction team then come, look, this structure is not approved for this weight of antenna, because this one antenna can weight, we have 4 beams, we have 4 slots, you'll have to install 4 different antennas in order to balance that structure. That is a requirement. So instead of using 2 quad pole antenna, you use 4 dual pole antennas. Okay, what is quad pole antenna, what is dual pole antenna, we'll explain in the next session for sure. Go through the antenna theory. Before that, I'm saying again, there's a document of antenna theory. Google it out as well. Note it down. The way I will check you guys if you are studying or not, I'll put up the questions of the topics which I'm recommending you to study. I'll put up the questions regarding those topics in the quizzes, and when you won't able to answer those questions, you will it will be obvious that you guys need to work on that. Okay, so we have to move towards the end of the session. I wanted to give another break, but this session is getting longer, so I didn't go break. Standard format of each session will be after each hour we'll have a 5-minute breaks and then we'll come back. So that will be a standard format. We will not able to follow this format in this session. Okay, so let's move on to the next slide. Okay, so So if you want to understand the environment, this is a good example of how the microsites work. There is a microsite. It is connected to the BTS. BTS is 3012. BTS 3012, if you can recall, is 3012 series is a UMTS series for Ericsson. There's a people talking. There's a train moving, and we have to provide a coverage to our mobile users, to the pedestrian, to the stationary in building. What is the design objective of that site? Is the our design objective is to cover that fast moving train as well? Then we'll have to optimize that site according to that. And there are a lot of other parameters which we need to know. So this diagram is just the environment of versatility. We have a mountains which we have to cover across. So we have to optimize our site and design our site according to that as much as possible. Best case scenario. This is another example of RF basics. I want you guys to understand when you look at the site what you are looking at as RF engineer. It's very important. So I will again explain you in the site what is what. This is our cabinets that can be okay. So you see these are the feeder cables coming out of those cabinets. These feeder cable are running on the cable tray somewhere. I don't know how. It's not so obvious in this diagram, and they are going into these antennas. So these are our antennas. These are called these antennas are a lot different. These are called dual pole antennas or quad pole antennas, but these are poles antennas. What are the pole antennas? We will cover in the next session. We'll cover in the next session to come. Yeah. So, and what is exactly this thing? This is also an antenna, but this is a microwave antenna. This connects the site with the RNC or the core network or MME. So this is not a cellular antenna. This is a microwave antenna. We use the term microwave antenna. So microwave. So this is a microwave antenna. So this is a basically part of transport network. This is not considered to be the part of cellular RF network. So we don't design this. These antennas we design, we determine what is the gain, what is the loss, how they are covering. So this is a part of RF engineering. So this is our cabinet. These are feeders going to the antennas. We have to provide the transport or the backhaul to our node Bs, microwave, fiber optics, copper, or any of them can be possibly based on the site or the availability to the operator can be used to provide the transport. Microwave is not very popular transport. The best popular or the most popular transport which provides very good quality for your network and the capacity for the backhaul is optical fiber. But every operator does not have, so based on their needs and limitations, they also deploy microwave. As RF engineer, we mostly required to design RF DAS and DAS. As RF engineer, we should understand ATOL. We should run propagation and ATOL. Based on that, we determine RFDS, because to reach RFDS is not so simple. There's a lot of design consideration, and after putting those design consideration and your goals. So there are two things. There's as RF engineer, in order to design an RFDS, you need to know what is your design objectives, what coverage you want, and what you can deploy. Maybe you cannot reach 20-meter height. You have to reach 15-meter height. Then you have to change the tilt according to that. Maybe your site is shooting too far and you don't want to go too far because it is causing interference it will cause an interference for other cell. So you want to down tilt it. So all those information, but you cannot down tilt it because of some reason beyond a certain degree. So all those consideration you have to take the best case scenario and put it in the RFDS, and you go to, that's a preliminary design. When it comes in, you iterate it and then put it in the planning tool, and then you arrive at the best design. And when you run the propagation on the design and you're happy with it, it looks good on the ATOL or the planning tool, you say, okay, it's good enough, I'll prepare the RFDS for it. So RFDS, or the radio frequency design sheet, is essentially can be a Excel sheet only, but it expresses the height and it has a standard format. We'll go through one by one what are the components of an RFDS. So first we will learn how to arrive at the RFDS, how to prepare the RFDS, how to determine what is the quality requirements, what is the coverage requirements, how do we do RFDS. So then we'll be ready to do RFDS. Then we'll study what are the components of RFDS. We learned from our previous sessions that in RFDS these are the requirements, and to prepare our RFDS completely, we need to prepare uh, uh, we need to understand our coverage goals. It's met, it's not met, and then we prepare the RFDS. Once RFDS is prepared, RNDCIQ is more of a soft parameters and data fill job. So in order to communicate it to the scripting team, I explained it to you guys. RNDCIQ is used to communicate it to the scripting team or the UTron or EUTron engineers to program the node B according to that. So you put all those information in the RNDCIQ, send it to them. You send the RFDS to the construction team so that they can construct. But before you prepare the RFDS, you do not go sit blind and start preparing the RFDS. You have to meet with the construction guys. They tell you the limitations and the requirements, like the limitation of the height, limitation of the cabinet, because the cabinet determines the capacity. Maybe they cannot, you want more capacity, you want 2 cabinets over there, but they can put only 1 cabinet. So it means there is less capacity for you available. So in terms of capacity, it will affect the height, will affect the coverage and the quality, and the backhaul is not big enough for you, so it will affect the capacity, what throughput you can achieve on the site. So all those consideration you have to consider before you finalize your RFDS. Okay, when you arrive at RFDS, then you go to RNDCIQ. Will we generate RFDS in the course using ATOL, etc. in the next session, right? We will learn ATOL in the next sessions to come. We will learn the ATOL for UMTS. We will learn the ATOL for LTE separately. And then we'll understand what is the requirements for LTE, what is the requirement for UMTS, what kind of antennas are there, how the site is done. When we'll go study case by case basis, then we'll understand what is the role of ATOL and the planning tools is there, what is the basic body of knowledge and understanding you guys need, which will be transferred during those sessions. Once you understand those ATOL and those sessions, then we'll study RFDS. Then we'll start studying RFDS in the next sessions to come. It will not be in the next session. It will be in, maybe we have total 6 sessions planned. Maybe it's for 4th session, I believe, or 5th session in the RFDS comes in. So RFDS, there will be separate sessions for RFDS of macro sites and the DAS sites. So let's move on to next slide. I believe that answers your question. Thanks. Okay, so now our next slide is another example. We can see there are a lot of microwave sites and there's antennas, so you should be able to identify. If I ask you, point me the what is a cellular antenna, you should be able to easily tell me, okay, this is a cellular antenna, these are microwave antennas, these are the brackets, the smaller, why this is smaller antenna. Okay, if you see a smaller antenna and a big antenna and both are cellular antenna, you should be able to tell 2 things. Maybe the frequency is higher, so if the frequency goes higher, the size of antenna goes smaller. Maybe the gain is smaller. If the size of the antenna is smaller, the gain is smaller. Why the gain? Gain is affected with the dipole antennas. So steady antenna theory, we'll discuss antenna theory in detail in the next session. But I will expect you to have some good foundation of basics of antenna theory. That's why I'm continuously stressing, read the document which I sent, Google it out, study antenna theory, so we can discuss at the advanced level in the next session. Otherwise, it will take too much time. Okay, now this is another example, just a study for reference. This is another example on the top of a tree. This tree can be a fake tree. Why such things are done? Because the community says it's not beautiful. The antenna, our tower destroys the beauty of the community. Then you'll have to install something like a tree to install the antenna. It adds to the cost. but in US and other Western countries, beauty and the aesthetics importance are very important. So there are a job which is called zone engineer. Okay, there's another domain of the job which is called zone engineer. Note it down. The job of a zone engineer is to design, to get the approval of the community or the municipality or the people in the municipality. They come, you tell the community, they sit in the municipal hall, and the municipal hall you have to go and explain why it's required, why is it beneficial, and make them agree with you. And they say, okay, we agree with you, but you have to don't look bad. My the surrounding should not look bad. Install an antenna. So that's the job of a zone engineer. Once you become a design engineer, zone engineer is not very much difficult. He has to use a tool, but he has to be a very good communicator because he has to go and talk to the community, right? So that's another job. Remember, especially in US, there is a job for zone engineers as well, and it's considered to be a specialized field, but it's very boring because it does not require more technical knowledge. Rather, you should have a good people and persons skills. Okay, jumping back, so we discussed cells, sectors, and carriers. Okay, so before we move on to the advanced levels in the next sessions, you should have a good understanding of these terminologies. If you don't, I'm trying to explain over here, listen carefully. If you don't, by the end of this session, shoot me the question. We have a blog or the group where you can share your questions. At the end of the session, I'll send you the Facebook group. We are creating the blog. The blog will be up soon as well. If it doesn't, ask Muslim why it's not up, but it should be soon up soon as well. You can put the questions over there. I'll look after those group, the Facebook group. I will send you at the end of the session. You guys can join that Facebook group, and we can you'll hear from me about your answers over there. Okay, we hope blog will come up soon, Muslim. Yeah, we sure do. Okay. A sector. What is a sector? Okay, a sector is based on a direction of antenna. If you have three antennas, you have a configuration of 0, 120, 240. So one is pointing to 0 degrees, 0 degrees with respect to the north, 120 degree and 240 degrees. Then you say we have three sectors. If you have two sectors, you're saying one is 0, one is 180, or one is 0 and one is 240. It depends. Okay. If you go back to the previous slides, you see over here it is 0, 120, 240. If you go to this slide on the planning tools, it looks something like that, 0, 120, 240. So what is 0, what is 220, what is 240? Okay, so this is one of our examples over here. This I believe is not, it's 30, then you add 150, and then you add 120 to 150 is 270 or 280, whatever you add. So these are three sectors at different antennas. Different operators in different markets follow different standards of these sectors, but it's very important. So direction of antenna determines the sector. Okay, it does not determine how many carriers are there. It does not determine how many cells are there. Okay, so don't be confused. So what is basically a sector? A sector is based on the direction of antenna. There can be many cells, or there can be. Okay, I did a mistake. No. Okay, no, I have. Thank God we have the recording on. So we have we can have more than one cells or carriers in a sector. We can have only one cell or carrier in a sector. Cell are the logical entities, and every cell has a unique cell ID. Especially unique cell ID and lac combination are always unique. So in a network, UE identifies a cell. Okay, whenever UE is communicating, it is communicating with one cell and it is measuring other cells. It may be measuring other cells. It may be measuring the cells on the same frequency. It may be measuring the cells on other frequencies, but it's measuring one cell. In UMTS and LTE, it's a little different. In UMTS, UE can be connected with more than one cells at a time. In LTE, it's always connected with one cell at a time. So in LTE, in UMTS, theoretically, write it down. In UMTS, theoretically, a UE can be connected with 6 cells at a time, and it means it will be sending and receiving communication with the 6 cells. Practically, that is limited to 3 cells in all the networks. That is a configurable parameter. but it will be measuring other cells other than these three cells. In LTE, it is connected with one cell at a time and it measures other cells. When I say measure other cells, it can measure the cells within the same frequency, it can measure the cells in the other frequencies. It always measures a given number of cells in the same frequency. In the other frequency, it only start measurements once it enters compressed mode. Okay. What is compressed mode? So in order to make the measurements on other frequency or other UARFCN or EUARFCN, UE has to enter the compressed mode. Remember compressed mode. I'll ask in MCQs, you will find this word compressed mode and asking the questions about compressed mode. Compressed mode is when the quality on the quality on all the cells which are serving you currently goes so bad. They are on the same frequency, but none of the cells measures the quality threshold or the coverage threshold. Let's say it's going beyond minus 98 dBm or the quality is going beyond minus 12 dBm. Then you have to, in order to maintain the call, have a good not to drop the call and have a good subscriber perception, you have to try to save that call. So what do? You start to measure other frequencies. So there are other neighbor defines on other frequencies. There are other network, like you're on LTE, you will try to go hand over to UMTS. So that's what you basically do. Sorry guys. So that's what you guys basically do. So it will enter the compress mode. Compress mode means it is doing signal measurements on other frequencies, that how does the signal strength of other frequencies which have been already defined as my neighbors, but neighbor on other frequencies, how does they look like? Should I make a handover? Should I not? All those algorithm starts to run. So there's a compress mode as well. So any questions about compress modes? Okay, so your assignment to study compress mode in LTE and UMTS. Compress mode is this only during bad network coverage? It's yeah, it is during bad network coverage. If the coverage from all the cells which are on the same frequency goes below a certain threshold, or the quality is bad, also, or the quality or both goes bad, either or both goes bad beyond a given threshold of coverage and quality, which are mostly the subject of optimization. So it enters the compress mode to measure other frequencies. Other frequencies can be on the LTE other carriers, or it can be other technology as well. So if you are on LTE, it can start measuring other carrier of LTE, or it can start measuring UMTS, other technology. So these are all based on, but for either to measure on other frequency, it has to go on compress mode. Either it has to measure uh, within the same technology, other frequency, other carrier or other UFCN, or within the other technology. It has to enter the compress mode. So mainly the UE searches for better cells to handover. For both handovers, and when it's in idle mode, it keeps, if the quality of the cell is not good enough in the idle mode, it's for cell reselection as well. So there are two concepts: idle mode and the connected mode. So in idle mode, it's cell reselection, and in connected mode, it's handover. Remember that. So yes, for both idle mode and connected mode, both for cell reselection and handover. Okay, but the criteria for handover and idle mode cell reselections are different. They are not the same criteria, in fact. So, and the algorithm, how it's handled by the network or the RNC or the node B are also different. Okay, we will explain it. Maybe this will more explain in optimization course rather than here. You can search it on the Google device. Okay, so if two cells have the same PSC in the UMTS and the PCI in the LTE, but different URFCNs, in that case UMTS and URFCN in case of LTE, then they are different cells and different carriers. Any questions about this point? Or you guys can understand this? Like, what it basically is saying is basically this point. What it's trying to emphasize is as long as your scrambling code is different and PCI is different on a cell, and your URFCN is different, you're logically different cells. So carrier and cells are logically the same, but if each cell in the sector have the unique URFCNs, so what it's saying is carrier and cells are logically same. Okay, so and each two cells can have same URFCNs. Okay, remember, cell can have same UARFCN. Okay, but two carriers cannot have same UARFCN. And this is true for both LTE and UMTS. Okay, remember that. So, and logically, each so remember this thing. Yeah, I'll explain later. Same carriers have identical URFCNs. Yes. So if I say it's a first carrier, then all the first carrier will have the same URFCNs. Remember that. If I say, and this is true for both LTE and UMTS, if I say it's a second carrier, it means first carrier had the different URFCN and second carrier have the different URFCNs. But if we go down, it will, I'll able to explain better. If we go to the next slide, you see there are cells. Okay, these are sectors. This is one sector. Every side has three sectors. This side has only one sector, but it is an omnidirectional site. It has it has three sectors but two carriers. So if you look at it, in detail, you'll able to see. You see, there are lines 1, 2, 3, 4. So these lines graphically on the map, how to represent different sectors, that's how it's used. This has two sectors. This has 1, 2, 3, 4 sectors. This has 1, 2, 3, 4 sectors. This is 1, 2, 3, 4, 5 sectors. This has only single sector. Okay, so different sites have different sectors. So each sector has a unique identity, but the thing is, each sector is identified by URFCNs. So I don't want you to carriers are identified by URFCNs. So cells are identified by cell ID and PSC or PCI. Okay, so if I go to the next slide, so we have three sectors, and each sector have 1, 2, 3, 4 carriers, and there are on the right you can see their URFCN's number. On the right you can see their URFCN's number 1, 2, 3, 4. So on the right this is 642, 487, 512, 4360, 4385. Okay, each URFCNs represent different frequencies. So this has 5 carriers, 5 carriers. This site has 4 carriers. This has 4, and it's only single directional. This has 5 carriers. So the colors, each different colors represents different carrier. Okay, but each different direction represents these are 3 direction represents different sector. So each sector has, in this case, it has 1, 2, 3, 4 carriers. In this case, each sector has 1, 2, 3, 4, 5 carriers. I hope difference between sectors and carriers is understood. Carrier is used to extend capacity. Exactly, carriers is used to have more capacity in the network or on the side. Yes. So why we add carrier? Yes, to have more capacity. How many carriers could be per cell sector? Well, again, this is a more into a RFDS question. We have a node B limitation. Okay, a node B, when you add carriers, automatically each carrier represent a cell, right? So if I ask you, it is a 5 carrier site. It has 3 sectors. How many cells are there? For example, can anybody tell me how many cells are in this site? How many cells are in this site? Can you type? Start typing. 16. 1, 2, 3, 4. Okay. Anand. Okay. 12. Khalil Lagari 12. Okay. Other guys, Nakvi 12. Okay. Okay. Khalil, you change your answer, man. Come on, man. Stick to one answer. Okay, second one. Okay. Say Mashoot 4 cells per sector. No. 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 Okay, guys, don't change your answer. Stick to one. Okay. Now I will reply you. I'll reply you the correct answer. This site has 12. Simple. It has 3 sectors. 1, 2, 3 sectors. It has each sector has 1 carrier. Each sector has 4 carriers. Sorry, 1, 2, 3, 4. So each cell has 4. Each sector has 4 cells. Okay. So each sector has 4 cells. It has 4 multiplied by 3, 12. Understood? Or are there any questions? Understood? If any questions, I'm waiting. Okay. Oh, okay, guys, we are 12 minutes over time. So I want you to start typing how many sectors are in this site. Okay, start typing right now. We don't have much time. Come on! I just told you this one has. I just told you this has 12 cells. This one has 12 cells. So how much this has? Yeah. Now everybody is right. 3 sectors, 15, 15, 15, 15. This one, because it has 5 carriers. 1, 2, 3, 4, 5 carriers. Okay. Okay, guys. So this is the one. So we have to move towards the end. Okay. Now DAS. I'll have to go through the DAS little quickly. It's later than. So the process in the DAS remains the same. What is the DAS? DAS is not an air interface technology. DAS is not an interface technology. It's a signal distribution technology. Why it's used? In order to cover places where macro cells or the tower sites cannot reach. DAS is designed, especially indoor. There are some outdoor DAS as well. Okay. So how the DAS looks like? The design process for the DAS, the flow is same, which remember the old one, it has not changed. The steps are still same, but the process in its detail is entirely different. Okay. So there's an example of IDAS. You guys see over here. You guys are able to see over here. These are the remote units. These are connected with a fiber hub. This is service. This is a repeater signal, and this is a repeater signal. How we are feeding the signal into the DAS system using a repeater. Repeater is receiving its signal from, in this case, sorry guys. Repeater is receiving its signal in this case from repeater is receiving from the other macro site. Okay. In this case, it was receiving from other macro site. Okay. Instead of installing a macro site, we can feed this signal by our base station. We can remove this. We can install a RBS or node B and feed the signal. Theoretically, we can do that as well. So this is our options. Yeah. There is no microwave antenna. This Yagi antenna is representing there is a macro site. Okay. So what it's basically doing is receiving the signal from the macro site and amplifying that signal and distributing it within the building. Okay. So there is pros and cons for everything. So installing a DAS system like this, it will improve the coverage, but it will not improve the capacity. Okay. Remember, using this is called donor antenna. You will, when we'll study DAS, this is called donor system or donor antenna. So it will coverage is improved, but capacity is not improved in this case. Unless you install a RBS, then both capacity and coverage will be improved in that case. If you install a RBS over here. Okay. This is another system just to give you a physical feeling of how it's done. What coverage improvement in meters per dash? I didn't understand your question. I'm sorry. Can we keep this question for the last? Okay, so this is RBS. So this is another example where there is no donor antenna, but we have installed a RBS. Okay, the RBS is installed at the bottom. RBS is installed at the bottom, and there is a remote units which have been installed at every floor. You can see around 6 remote units, and there is one RBS feeding all the 3 buildings. It's possible. This is one of the example. It's very dynamic field. There, it can be very different for every one of them. It's a conceptual thing. This is an example. Like you have RBS installed over here, and then you're distributing the signal in the building. So because the building is spread over, you have a different, if it's a tall structure like previous one, you decide to have one RBS feeding all the 3 buildings. It can be different based on that's what we will learn in the DAS system. In the DAS system, we will learn based on the building structure, based on our requirements, how we should deploy DAS, how should we position our antenna, what is a floor plan, what is a design plan, how the IB wave is used, how to run the propagation, how to do the link budget, what is the criteria for DAS, how to calculate the DAS system, how to prepare the RFDS, how to prepare the design in the IB wave, how to understand the design in the IB wave, how to calculate we will not go into the detail, but how to calculate the link budget. We will go into very much detail, every single detail of how to calculate the link budget, how the link budget is being calculated for DAS site. What is the criteria of calculating the link budget for the DAS site? What are the components of the DAS site? There is an optical RF converter, there's an access point, how the signal is being transmitted. This is a graphical description how the signal is going. It gives you more engineering details when the RF signal, when the electrical signal is converted to optical signal on the fiber. And then over here, if you see, there are this is your access point, which can be your base station as well. This can be node B. Essentially, it's sending the signal to RF optical converters. Basically, these are converting an electrical signal into optical signal, and this optical signal is going to the RRUs. RRUs are where the power, they amplify the signal and send it to the mobile. Okay, remember that DAS is essentially a repeater only. Okay, the node B does not know it's feeding a signal to DAS or a macro. UE does not know if it's receiving signal from a DAS or macro. Okay, but as a RF engineer, you know that this is a DAS system, so you plan this system in a way and its components that the coverage is required, and there is a seamless coverage for this our user. Okay, but how it is done, what is a splitter, what is optical converter, what is RRU, how it is designed, what is the RRU capacity, what are the parameters we have to calculate. This is a subject of this design course, and there is a complete sessions on or chapters on design of DAS design or distributed antenna system design itself. Okay, I see. Is there any questions? What coverage range of DAS RRU antenna? What coverage range? I don't understand. What coverage range? How far they can cover? Is that your question? DAS? Well, it depends on your design, right? It depends on your design objectives, how far 1 RR you can go, what is the building structure, is it indoor or outdoor? So it depends on manufacturer. You will have to understand those factors before we can answer how far the coverage will go. And that is the purpose of our engineering, to design a coverage and know from the design how far this coverage will go, what will be the quality, what will be the capacity, should we install it, what is the cost, and then go ahead and install it. Okay. So this is if you run the indoor coverage, that's how it looks like. We saw macro coverage. This is especially for indoor. Yes, this is especially for indoor, because we have as our course covers both macro sites and DAS sites. So we already saw, if you guys can recall, how the coverage of a macro look like when you run on a planning tool. This is a rough example. Actually, it looks a lot better, but this is a rough example of how it looks like. We will, in our training videos, which we will share, you will be able to see all the coverage, how it's run, how it's done. We will discuss it in detail, how it's done. So that's how we plot the indoor coverage as well of antennas. These are one of the example of our omnidirectional or IDAS antennas. That's how they look. Maybe if you are inside a big building, you'll spot it on the roof of the building, on the ceiling of the building, pointing inside the building to give indoor coverage. To give you a feeling of how the systems are, there are indoor IDAS and there is ODAS as well. Why ODAS? Because sometimes the macro sites, you don't have the permission to install big towers somewhere, or your design objectives are not met with the big towers. Then you install outdoor DAS as well. Okay, so you have a base station, that base station feeding signals to small antennas around, and they are small antenna. They are under the coverage of macro, because whatever is there, remember there may be a macro which is covering, which will be covering part of it or whole of it, but there will be some weak macro coverage. But you make sure that these antennas are dominant server for this UE, because when you plan, you know what is the coverage of all of these antennas. Okay, so you plan those antennas. If this macro coverage coming in, the macro signals coming in, then what is the strength of this macro? You have to plan all this, which will know. Walkthrough test. Sorry for the question. Let me see the question once again. Walk test or walkthrough test is used for DAS, usually for DAS, because you cannot go and drive the car inside a building or small places, so you have to walk through those areas. I believe, Arshad, your question is, does it increase handover between DAS sites and the macro sites? Am I right? DAS sites, does it increase handover between DAS antennas? I don't understand your question. Does it handle the one of the main criteria of design is not to overlap the coverage too much between any sites, macro sites or DAS sites, or two macro sites or two DAS sites. If you have a overlapping coverage with the similar signal strength, we call it pollution, and we will go through the concept of the pollution in the design, but it's majorly subject of optimization. It's called pollution, and we have to avoid pollution in our network design. So it's easier for us to optimize, and it increase, if we have a overlapping coverage, it will increase the handover. So coverage is designed in a way that the cell is dominant. The cell which is intended to cover a given area is dominant in that area, and it's not dominant in another area, and that is whole purpose of our design. Yeah, we have a pilot pollution. If we have overlapping coverage, that creates pilot pollution. Yes. So this is a schematic diagram. This was basically a floor plan, which we will study then how the prediction is run on the floor plan. This is a type of antenna. This is our outdoor coverage. How does the outdoor system look like? This is a schematic diagram of link budget, or we call it link budget diagram or design plan. In IB wave term, this is called design plan. We'll study the components of the design plan, the link budget, what is a power splitter, what is the combiner, what is a duplexer, how we monitor, how we set the power for the remote units, how we feed the power from the BTS. Uh, Means all those questions like the power coming in from the BTS. We have a uh, DAS controller which this is converting from electrical signal to optical signal. This is a monitoring terminal for DAS equipment, and this is our DAS splitters, hubs, and then it is our remote units. Basically, this is RU, or the remote radio units, which are feeding, converting optical. This is optical or fiber cable. This is coax or electrical cable, and it is converting back the signal from optical to electrical, and we are feeding to antenna, because you cannot feed optical signal to an antenna, right? So we are moving towards the end almost. We should, because we are 30 minutes over our time. I'm really sorry, guys. This was the first session. Next session, I'll try to keep it. This is another example to give you a good view of how this schematic looks like. Just a feeling, not exactly. It just give you a good feeling. This is a comm scope. These are some of the DAS, one of the DAS system. Each of its components we will study in detail when we move to DAS. This is Corning. Why I'm saying Corning or CommScope? Why I'm not saying Ericsson or Nokia? Because remember, the DAS manufacturer and uh, cellular network manufacturer for standard equipment are different. There are different manufacturer for DAS equipment, Node B, E Node B, RNC, and they don't necessarily make DAS equipment, which are made by Tyco, Corning, which are different manufacturer. They can be same, but actually they are mostly different, and it's not requirement that DAS equipment manufacturer and the E Node B and RNC manufacturer should be same. That's not the requirement. So that's our flow of the course so far. If any of you guys have any questions, that will be end our session for the day. You'll receive the details from Mozam regarding further, if you guys would like to move on with the course training. There are a lot of things which we'll discuss. This is the first complete session which covers all the basics and what is required. In the next session, we'll jump on to the macro design, how the macro is designed, how the macro is planned, how ATOL is used, and all those details. So if you guys have any questions, I'm available to answer your questions. Okay, so no questions. We'll get the PowerPoint slides. I'm sorry for this. PowerPoint slides are proprietary. They're not shareable. You will get a hard copy at the end of the course or in the middle of the session if you request. We can send you out the hard copies, but it has some requirements. But Mozam can brief you on that. That as a company policy, I cannot send you personally the PowerPoint slides. Every one of us who has all of our sessions will be shared and we'll provide it to our users. Yes, to our student or audience, we'll provide them the individual accesses for all these sessions which we record and upload. Any other questions? Okay, guys, for any more further questions, Mozam will be available. info@mojosoul.com is the site. I will just hang on a second and I'll share you guys with our Facebook group where you guys should go and subscribe, and you can put your questions. I will be looking after that group myself. This is our Facebook group. Please go and subscribe. And you guys will able to see it there. There is something which Mozam I think wants to share with you guys. Okay, so I'll unmute Mozam and he wants to share something. I don't know. Yes, Mozam, go ahead. You can. Mozam. I hope he is able to. Okay, guys, over here, thanks a lot. We'll continue our session. I'll stop the recording. That's why guys can stay online and listen to Mozam's question, but I'm stopping the recording over here. Thanks all of you for being here. Really nice presenting you. I hope everything was fine. You will receive an email regarding test which has been done. So you will receive an email and you can get you will get an email link to perform the test. You'll have to come back to the Citrix session. The time will be mentioned. I had the plans to give you the test right now, but it's already too long. You guys go through all the topics. I'll try to upload the video, and you can go to the video and Google it out and go to the prerequisites material to answer those questions. You will have to, before the second session, you will have to go through the test, and you will have to go through the poll. I'm opening a poll right now for you guys. Please, just it's a simple poll, say yes or no, and we'll be done for the day. Thanks a lot for you guys for being here.